the sum, for example, of a point A and a point B lies somewhere out here for some reason, and the difference lies somewhere else. And if you don't know that everything is actually still attached to this origin here, and that we're actually talking about arrows, then none of these sums and differences make sense. And this goes back to Euclid's first postulate: 2 points determine a single line, and nothing else, right? The result of doing anything with 2 points must lie on the line spanned by those 2 points. So, to drive that home, the claim is that for any operation to make geometrical sense, in the case of points, any operation you do on them, a binary operation, should always produce an output on that line defined by the 2 points, because there is no other information. So this suggests a different approach. Instead of using different bags of real numbers and using vectors for everything, we will try to find one bag, and every element in this bag will be something that's geometrically meaningful. And hopefully we will also be able to do this in a way that we are not tied to a specific number of dimensions. Now the teaser is that by the end of this talk, only one of these vector quantities that I talked about will still be a vector by the end of this talk, and all the others will turn out to have been something else. So, first we need to define what I mean by geometry and what properties we want. So we want all operations to work in the subspace of their arguments. And we want to represent both elements and transformations within the same algebra. And instead of using an algebra of arrows, we want to use an algebra built up from reflections, because that turns out to behave the way we need. So there are 2 key topics I need to cover. That's something we call K-reflections and geometric gauges. So first, the idea of K-reflections. Starting in 1D. So if I have a point here, for example, and I reflect this green shape in the point, it ends up being the orange shape over here. And you can see it was a reflection because the head is on the other side. Right? I can also compose 2 reflections. And then my green shape would first be reflected over P1 to be in the middle here somewhere. And then again to be on the other side of P2, and now you see that the head is again on the same side, so it has really translated. And that's all you can do in 1D. Then when we go to 2D, you get something new, the line. So my green shape, I reflect it in the line L1, and it ends up being the orange shape over here. I can also then again do 2 reflections in parallel lines, and then you see that again the green line, green shape is translated into the orange one. And I can also now do something new. I can intersect them at an angle. And now if I reflect first over L1, I end up over here in this intermediary state, and then I reflect over L2, and it ends up being the orange shape over here. And effectively, my green shape has now just rotated around the intersection point of these 2 reflections, right? So that's another nice thing to have. But now we have a special case, actually, where if you choose these 2 reflections in lines to be orthogonal, then you would first get the green shape reflected over L1, so it goes to the upper left quadrant here. And then you reflect in L2, so then it ends up here in the lower left quadrant. But that's actually the same as just doing a point reflection, right? And that turns out to be crucial, because that means that actually we will be able to identify a point with those 2 orthogonal reflections, because they behave the same way. Another key point is the geometric gauges, and that is this idea that if I take my green shape and I reflect it through the first line, it ends up in the intermediary state, and then over the second it ends up in the final state. But all of these rotated versions of that reflection all give the same result. So I don't know which one it was, right? If I just show you the input and the output, there's no way for you to know which particular pair I used. And this is true so long as I keep the intersection point the same and the relative angle between these 2 lines. And the same is true for translations. So if I take my green shape, I reflect it over the first one, and then back into the orange final state, then no matter which 2 particular lines I used, you won't be able to tell the difference from the result. So that's a gauge degree of freedom. And that's again true so long as I keep the distance between those two reflections the same and their intersection point, right? And their intersection point in this case is the point at infinity where these two lines meet. Why am I telling you about these geometric gauges? Because they tell us how reflections combine. So if I take my square here and I reflect it 4 times, it turns out that that is actually the same as just doing 2. I'll let that play out again and explain what's going on. So we start with the original shape, I reflect it 4 times, but in each of these intersection points I have a gauge degree of freedom, right? I could just choose to rotate it differently. And I do that such that one of the reflections from each goes through the other point, and that means I've effectively done the same reflection twice. But doing the same reflection twice is the same as doing nothing, so it drops out. I might as well not have done that one, right? So I'll just let that play out one more time, because this is a vital point. So again, until it goes through the other one, 2 of them become the same, it cancels, and then it's just a rotation around this new intersection point, which you would have never been able to predict if you just see the original 4, right? So that's a very neat concept. And this is something called the Cartan-Giordani theorem, and that says that every orthogonal transformation in an n-dimensional embedding space is composed of at most n reflections. So Cartan-Giordani actually dictates how many reflections can be performed in a given number of dimensions. So if you are in 1D, you can do either a single reflection, you can do 2 reflections, which makes a translation, and then when you go to 3 reflections, that's the same as just doing 1. And in 2D, the same thing happens. You can do a single reflection, you can do 2 reflections, and that now becomes either still a translation or you get something new, the rotation. And then you can compose 3 of them to make a glide reflection. But then when you do 4 reflections, nothing new happens. That's the same as doing 2, as we just saw. And the same thing happens in 3D. Then at the level of 3 reflections, we get something new, the roto reflection. At 4, we get a screw motion. And at 5, we get back 3. So there's nothing new there. And from this idea, we can form our algebra of geometry. So starting in 1D, we want to have points and also point reflections. And we can do 2 of those to make a translation. When you go to 2D, you get something new, the line and the line reflection. But if you compose 2 orthogonal line reflections, as we've seen, that's the same as a point reflection. So that's not something new, and that's actually something I already had. I knew how to deal with points. So everything we had in 1D is now automatically included because I rediscovered the point in 2D as 2 orthogonal line reflections. And so everything from the row above of 1D is now automatically included. So that's very nice. I do, however, have something new because I have a line. So I can do some new things potentially. So if we explore that, 2 parallel reflections in lines form a translation. If the lines intersect, it is a rotation, that's something new. And if you combine 3 of them, you get a transflexion. And then if you go to 3D, we only get 1 new object again, the plane, and that's it, that's the only new thing. And then if you compose 2 orthogonal plane reflections, you get a line. And 3 orthogonal plane reflections act as a point reflection. So actually, everything I knew about lines is now applicable again, and everything I already know about points is also applicable again. So the only new thing I have is planes. And again, we start exploring what you can do with those. And then again, we find that we can make translations and rotations with planes. We again have the transflexion. And we have something new, that's a rotor reflection, so that's first a rotation, followed or preceded by an orthogonal reflection. And we have something called the screw motion, and that's 2 reflections that make up a rotation, and then 2 orthogonal ones that make a translation that's orthogonal to it. And this flavor of GA is called PGA. And that's our bag of numbers now. Now you're looking at it up to 3D. So just to show you how we work with just this a quick demonstration. So we happen to be in 2D here. So my points are actually the composition of 2 orthogonal lines. And so if you want to take the product, for example, between 2 of these points, then we know already what it should be, right? It should be a translation, because the composition of 2 points was a translation. And we know that that translation should be along the line that is spanned by the 2 points, right? So let's check if this holds. And the secret to checking that it holds is these geometric gauges. So what I can do, of course, is I can rotate each of these freely to pick whichever favorable I want. So I choose it such that the reflection from the red one goes through the blue point. And I do the same for the blue point until one of those reflections goes through the red point. And then the moment that happens, I've effectively done the same reflection twice. So those two just disappear. And I'm left with 2 parallel line reflections, which is indeed a translation, and it is the translation along that line, right? So this property now nicely holds. Another key point is then, how do I actually do a transformation? And that's something we call conjugation. And that is this sandwich operator, right? So to actually transform an element y by a transformation x, you have to act on it from both sides by x and x inverse, to be precise. That's a famous thing in group theory, but we can actually understand it again using the geometric gauges. So consider, for example, that I have a point BC, the blue point here, and I want to reflect it in the red line. So how do gauges end up giving the reflection of this point to the other side of the line? So the key thing here is, I should show you, I have drawn 2 copies of A, but you just couldn't see it yet. So the key insight is that, again, I have everywhere where 2 reflections touch each other, I have a gauge degree of freedom that I can freely manipulate. So I can freely move around each of these intersection points. Okay. I have to be very careful if I start manipulating them all at the same time. So what is the key insight that I will use now to do the reflection? The key point is that I will take the reflection B and I will rotate it into an A. And I will also rotate C into an A, because then I have 2 copies of A that touch each other, and that will collapse. And then whatever I'm left over with will be the new point B prime, C prime. So let's see if that works. So the idea is I take the line B and I will rotate it until it becomes A. And then I will rotate C until that also becomes the original A. And at that point, it disappears, and I'm left over with the reflected point here, where now 2 orthogonal lines intersect. Right? So that's actually explains very nicely how with the geometric gauges you can even explain how composition works. And so that's also why we say that these elements are basically, they double both as the transformation or the element itself. It just depends on if you act from both sides, then it actively becomes a transformation. So now we are ready to find the realization of this geometry. And there are some key observations. So the first one is, as we've talked about now, doing the same reflection twice is the same as doing nothing. So that means that if in this conjugation I act with a reflection R on an element X, and I do that twice, that should be the same as just getting X back. And that means that R, the reflection, should square to either positive or negative 1, right? The sign here doesn't matter. And the key point is that that goes for points, line, and plane reflections all the same way, right? And we know that in a Clifford or a geometric algebra, the products of orthogonal vectors square to scalars. So these are the blades. If you take the product of k different orthogonal vectors, such a quantity will always square to a scalar. And lastly, it is already also a well-known fact that the products of vectors in Clifford algebras make up something called pin groups. And those are indeed the groups of reflections. So we can realize these ideas of geometry that I've talked about now in a geometric algebra. I should still point out that we have to be very careful how we build this up if we are to get our dimension independence. Because remember the equivalence principle from Stevens' talk, if you can make it look like a duck, it'll quack. And actually, you might think you're looking at points here now, but you're not, right? These were actually, some of these were perhaps lines. And a key point here is that I start out looking at points here on a line, and when I add only one extra, if I rotate my camera in one extra dimension that suddenly turns out to be there, then what was originally the line that I'm looking at here will stay the center line, right, in this new space. But some of these things which looked like points are actually lines, right? So what was already a line will stay a line. What looked like a point will turn into a line. So that's the principle we have to respect. And so I start with the smallest algebra, R101. And in that algebra, I have vectors and bivectors, and that's it, plus the scalar itself. So the vectors I use now to represent points, and the E0 term, the one that squares the 0, is the point at infinity. And you can mix, and E1 is the point at the origin, and you can mix those two to make any point on the line. But now it turns out that these points I was looking at here in this 1D algebra were actually lines all along, as I just showed, but the line I was already looking at in 1D will remain a line. So what I do is I replace the scalar in the smaller algebra by a new vector, because I have to represent that line now as a vector, because everything that is a vector will become a line now. And so I get a new basis vector E2, right? And now I have all of these lines. And with the lines, I can again start making intersections to build up points. And then if you want to go to 3D, it turns out like, oh, this plane I was looking at the whole time, the two-dimensional plane, that was really a plane, but these lines turned out to have been planes all along, right? I just didn't see it because I was looking at it the wrong way. So again, I play the same game. I have to somehow represent the scalar, which was my plane. I have to start representing that now also by a vector, so that all the vectors are actually planes. And so then you get this algebra, where the vectors now represent planes. You can intersect two planes to make a line, and you can intersect three planes to make a point. And that's how this game works. If you stack it up this way, then everything behaves the correct way, in a dimensional agnostic way. All right, so that's now our realization of this bag of numbers. If I just care about the 1D bag of numbers, let's say, then I choose R01. If I want to include lines, then I have to go one up. And for planes, I have to go to R301. And it's worth noting that this particular view of GA is also referred to as the plane-based view. We've already heard that term in some other talks as well. So this is where I come back to the claim that actually elements of geometry are in general not vectors. Because as we see now, what traditionally we used for the point was a vector, but now we see that for a point we should actually use a trivector, and actually, to be more correct, we should use a pseudo vector. So we start counting from the other side, right? Because that way it will always hold in any number of dimensions. So points are actually pseudo vectors. Lines are pseudo bivectors, right? So you also have to count from the other side. Joining 2 points makes a line. If you formulate it that way, it will work in any number of dimensions. And the plane, that is still a vector, and that will always be a vector. And the same for my physics quantities. So if you are in physics, again, you see that these x coordinates, that's just a point, so that's a pseudo vector. And for the momenta, we will find that that is actually a sum of pseudo bivectors. That's something I'll get back to later. For spinners, I'm actually just going to kick that can down the road to David Eelbode's talk. So he will explain why those are not vectors. But I will still hint at them a couple of times during this talk. So now, the question I want to answer is, where was the geometry hiding all this time? So the first step in hiding this geometry is that we want to go to matrix representations of our Clifford algebra. So what you do, we know that in a Clifford algebra, the basis vectors commute this anti-commutation relationship. That is what defines the Clifford algebra. So EI, EJ plus EJ, EI should be 2 times the metric G. And the metric is a diagonal matrix with P ones on it, Q negative ones, and R zeros. That's just the technical definition of the Clifford algebra. And we wish to construct matrices that respect this same rule. So I want to make matrices, capital E of I, that satisfy exactly the same relationship, but now also I have to replace my 1 by an identity matrix. The way we do this is we start from some 2 by 2 basis matrices that capture the most essential properties. So I need a 2 by 2 matrix P that squares to +1, a Q that squares to -1, and an R that squares to 0 in matrix terms. And then you can start building up your matrix representations by taking this Kronecker product of the 2 by 2 identity matrix, one of the signature matrices, so that's a P, a Q, or an R, depending on which square you want, and then some of these I primes. And all the details to this are actually in the paper, Graded Symmetry Groups, by Stefan and me. And I will now skip over some of the extra stuff you need to do to get these matrices in exactly the preferred order, but the details are in the paper. But now we are ready to start hiding our geometry. So you start with a multivector X, and this multivector has a scalar part, it has a vector part, a bivector part, a trivector, and a pseudo-scalar. And I've separated out every time the part that's origin attached and the part that's at the horizon at infinity. So, for example, for the vector, we have E1, E2, E3, that is a plane through the origin. And then I have the last part, E0, that is the plane at infinity, the horizon. Right? And the same is true for all of these. So that's where this notation comes from. So I have a line through the origin, and I have a line at infinity. I have a point through the origin, which is the origin, and I have a point at infinity. All right, so now if you actually make the matrix representation of this multivector, it looks like this humongous mess, right? But the neat thing about this matrix, so this is a matrix that behaves exactly the same way that our multivectors do, and now just with the matrix product instead of the geometric product. And you notice perhaps that this first column of the matrix is all of the coefficients of our multivector in order with positive signs, right? So I could actually also say that I will represent this multivector with a vector. I just throw away everything else. You just keep this first column that also represents the same information. So what you can do is, instead of saying I have a multivector X and a multivector Y and I want to multiply those, I instead say I take a multivector X and I take a vector that represents Y, right? And so then I can replace my matrix product with a matrix vector product. And that's computationally much more efficient. And then the final step that we need here is I should also take the matrix representation of a rotor, right? Because now I want to rotate, for example, or rotate or translate my multivector X. So in GA language, we have this two-sided conjugation, the sandwich product. And now instead, I want to represent that using these matrix representations. And what's more, I want to represent it as this one-sided product. So I want to find some matrix A, such that if I multiply A on the multivector X, represented as a vector, that it has the same effect as doing the two-sided conjugation. And if you actually work that out, then you find that you get this type of block diagonal matrix. So most of this matrix turns out to be zeros, and just along the diagonal you get some interesting stuff. R is the rotation matrix, and T is a translation vector. So the easiest one to look at here is this block, perhaps. That's the most familiar looking one, perhaps. And so now, because of the fact that it is now block diagonal along the diagonal, we can actually just represent the action of each of these sub-blocks on its relative vector space, right? So I can say, oh, for points, I see now that for the point part, I get this 4x4 covariant representation, as it's called. So to transform a point, I could now take the vector representing the point, act on it with this 4x4 homogeneous matrix, and then I get the updated point. For lines, you have this 6x6 adjoint representation. And for planes, we have a 4x4 contravariant representation. So actually, I can now present a how-to guide for hiding geometry. If you want to hide geometry, you first switch to matrix representations of the multivectors. Then you throw away everything but the first column. You rewrite conjugation into a one-sided matrix product, matrix vector product. And then you recognize this block diagonal structure, right? And you just write each of those blocks down, acting on its own vector space. And then you can make $1 million for big linear algebra. All right, but do you guys hear that? There's still some sniggering somewhere. I think we might have missed someone. Is somebody still hiding? So let's look again at this bivector part. We know that lines have to be the meet of two planes or the join of 2 points, right? That's how you make lines. But if I make a general, if you make a line that way, then the wedge of it with itself should be 0, and that's something called the Plucker condition. But if you make a general bivector B, it will not obey that criterion. And actually, the simple example is if I just take alpha E23 plus beta E01, then if you compute B wedge B, it is not 0. And so that means that if I give you a general bivector, that won't be a line. So it's not an element of geometry. And in fact, it turns out that there are 2 lines hiding within this bivector. And for those familiar with representation theory, this might also seem somewhat strange, because if you take this adjoint representation, so I have the origin attached part of the bivector, so that's a line through the origin, and I have a line at infinity part, and it transforms under this type of a matrix representation, then if you look in the literature, they will say that such a matrix is reducible, but it is also indecomposable. But we know that can't be right. So hold my beer. Let's decompose it. So that brings me to the second part, finding these last holdouts. So the question is there something beyond Cartan-Giordani that we might have missed? So first you notice here, if I do a reflection in a single line, so what this illustration shows you is how far a point in the space will move under this action, right? That's what it represents. So a point very far away from the line will move a lot because it has to go all the way to the other side. But a point close to the line doesn't really have to move, and points on the line don't move, right? They stay in place. So that's how you should look at this visualization. So now if I do 2 reflections, then you see that you start to get a rotation around the intersection point, right, as expected. And now you notice what is left invariant now under 2 reflections. That's only this point, right? Everything else has to move around the point, but the point in which these 2 reflections intersect, that's your rotation axis, that remains fixed. But now if I do 3 reflections, something weird happens. Because now I have 3 reflections in these particular lines, and what is left invariant here? If you look at the graph, you do see something appear, right? It does seem like there is a line around here where things don't really seem to move that much, right? So there is still some structure here. And it's neither of the 3 lines I started with. None, I should say. So it is this line, right? That line is still invariant under these 3 reflections. Now, how do I find that line? That is, again, a geometric gauge problem, right? Because I have these 2 lines which are intersecting here from my 2 reflections. So I can actually gauge that, right? I didn't change anything, nothing moved. And now, one of those original lines has become the invariant line, and you see that I still have two parallel lines, so there's also a bit of a translation going on, right? And these things are completely orthogonal to each other, so they actually don't have anything to do with each other. I'll just let that last part play out once more, if it works. Never mind. Oh yeah, there we go. So just by gauging it, I didn't change anything in the plot, and we found the invariance. I can play the same game now with 4 reflections. So that's with a screw motion. So say I have this cube, and it undergoes a screw motion, so a corkscrew. That corkscrew can always be decomposed into 2 reflections representing a rotation, and they leave only this one line invariance, right? That's the rotation axis. But if you think about it, that rotation axis is still a one-dimensional subspace, and that whole subspace is left invariant under that rotation. So I can still do things within that subspace, and it won't be manipulated by the rotation. So for example, if I take 2 points now on that line, and I do 2 point reflections in those, then that will still be allowed, and that will give me a translation along the line as well. Right? And if you view it in the full 3D, those 2 point reflections on the line are actually 2 parallel planes. Right? So now I have found 2 intersecting planes that give a line, and then orthogonal to that I can still do 2 plane reflections as well. And the nice thing now is this screw motion turns out to be the product of 2 different commuting by reflections, and it leaves 2 lines invariant, right? So the first one is obvious, that's the rotation axis. But where's the other one? That's the line at infinity, where these 2 planes, the parallel planes, also intersect, right? So you get one line here and one at infinity, and they are orthogonal to each other, and they are the invariants of the screw motion. And that's something known as the Mozzi-Schall theorem, which states that every rigid body motion can be decomposed into a rotation around, followed or preceded by a translation along a single line, right? And now I want to make this sentence a bit more rigorous and a bit more general to see what's really going on here. A rigid body motion, we now have a new term for that. We would call that a quad reflection, the product of 4 reflections. Followed or preceded, we also have a word for that. That means commuting, right? The order doesn't matter. And rotation or translation, rotation and translation, that means by reflections. So if you want to generalize this phrase a bit, you would say that every quad reflection can be decomposed into commuting by reflections. And now suddenly it doesn't seem to have that much to do with 3D geometry per se anymore. This might also hold, and it does indeed hold, for example, in space-time. So we can actually generalize this idea now, and that's called the invariant decomposition theorem. So every K reflection, every product of K reflections can be decomposed into ceil K over 2 commuting parts. And if done this way, it works for even and odd K in any number of dimensions and with any signature. And we also find closed form exponential and logarithmic functions from this. And these commuting terms that we find here, those will turn out to be elements of geometry again. And so the cool thing is that the invariant decomposition theorem actually says that there is nothing new, there are no new isometries after the bireflections. So in 1D, you can only do 1 reflection or 2 to make a translation. But in 2D, so after you do 1 reflection, you can do 2 reflections to make a rotation or a translation. But then when you do 3 reflections, that's actually the same as doing 2 plus 1, right? So not 3. 3 is not a new thing. You get 2 and 1. So that would be, for example, in this case, always a translation with a reflection, as we've just seen. And in 3D, it's the same thing. So 3 reflections is actually just 2 plus 1 in an orthogonal space. And 4 reflections, like I showed you with the screw motion, is again 2 orthogonal bireflections. So there's nothing new. If you understand the basic bireflections, you understand everything you need to know about isometries. And so you might be familiar with the famous song ABA by Michael Jackson. ABA, easy as 1, 2, 1, or simple as do, re, do. Right? So this is a good mnemonic for the fact that nothing new happens after that. So now that brings me to the more formal part about what I mean by invariance exactly. What does it mean to be an invariant of a K reflection? Well, if I define conjugation, just to have a shorthand notation, so conjugation of X by R, I just write that with these square brackets, R acting on X, for a shorthand notation. So what do I mean by invariance? Well, if you transform something, it doesn't transform, right? So if I transform X by R, it should go to X. It doesn't change. And you could be a bit more lenient and say, actually, I also accept the fact that it might change sides. So the sides of the plane might turn around, but it's still the same plane. So we also accept that as an invariant. So that leads to a related question. What are the eigen L reflections, X, of R? So you have X, which is itself an L reflection, right? So that's one of our elements of geometry, for example, or another transformation. Which ones are eigen? So that now means they can have any eigenvalue gamma. So that's the more general question to ask. And now we find something really neat. If X is itself also an L reflection, then that means that its norm is a real number. And we know that the transformation R is norm preserving. So that means that if I act with R on the norm of X, so that's X squiggles, that will be the same as X squiggles, right? But I also know from the eigen equation, the eigenvalue equation up here, that it should also be equal to gamma squared the norm. So the norm is both equal to the norm under the transformation, but also to gamma squared the norm. So I find this particular expression, the norm of X should be the same as gamma squared of the norm of X. And so that leads to one obvious conclusion, and that's like, oh, gamma squared must be 1. But there's another solution, and that is what happens if X has a norm of 0. That's also a valid solution here. And the cool thing is that there live the spinners in the null elements with a norm of 0. So I think that's a really deep point to make, and David Ilbode in his talk will go more into that space of solutions. But the cool thing is, I think, if you are going to be a non-trivial eigenelement, so you don't have just a simple plus or negative 1 as eigenvalue, then you have to be null, which is pretty fundamental. But we know already that our elements of geometry, our points, lines, planes, they are typically not null, right? If you square them, it's just usually plus or negative 1 if you normalized everything. Unless they happen to lie on a horizon, right? The points on the horizon or planes on the horizon, they are null. But in general, the ones in our space will have a real norm, a finite norm. So they must be of the type gamma squared is equal to plus 1. And so that means they fall into one of two categories. If gamma is equal to plus 1, then if you work it out, that's equivalent to saying that the element X should commute with R. And you can also have, if I allow for, so those are called orientation preserving, right? The plane, the size of the plane, if it has some hair on it, that keeps pointing the same way. But you can also have orientation inverting. That happens when gamma is negative 1. And then you find that that is equivalent to saying that X should anti-commute with the transformation R. So the simplest example is a reflection itself. A reflection A is the invariant under the reflection by itself, right? Think back to the quiver plot I showed you with all the arrows moving. If you did a single reflection, then that reflection doesn't change. And we also, we say that A is an eigenelement to A, and it characterizes the transformation. Now, it's also worth pointing out that there are also orthogonal vectors, and orthogonal vectors, so an orthogonal vector C, anti-commutes with A, right? We have seen that before in some other talks as well. So if I act with A on C, that gives me negative C. But such an element we started calling ander instead of eigen, meaning other, right? Because it is invariant, but it's invariant because it has nothing to do with it, right? So that's not really eigen because it doesn't characterize the transformation. I cannot reconstruct that transformation if I just know the element C. If I just give you C, there's no way for you to know what the reflection was. And the reason that we needed a new term for this is because there's an infinity of such unhelpful invariants if you go for the dimensional independent mindset. And because there's an infinity of them and they all don't help you characterize the transformation, they don't deserve to be called eigen. Eigen means you characterize the transformation. Okay, so now we go to the next step up, that's the bireflection. So what are the invariants of a bireflection? If I have a bireflection UV, then we know from the famous formula we've seen a lot already, U times V is U dot V plus U wedge V. So that's a scalar quantity and a bivector quantity. And if this transformation is a rotation or a translation or a boost, so a boost is a rotation that mixes a time dimension with a spatial dimension, then these are generated by a bivector. And that bivector is going to be proportional to U wedge V. And such a B always squares to a scalar, lambda, right? And so we can always write those as exponential functions. So if you have such a bireflection, so a rotation, a translation, those are always exponential functions. And this is worth pointing out that actually there's no need for conditional statements of the different cases for rotations, boosts, and translations, because if you say the dot part, U dot V, is the cosine part, and if you just work out that series, you find that that's the cosh function of the square root of B squared. And if B squared is negative, then this corresponds to a rotation. If B squared is 0, it becomes a translation. And if B squared is positive, it's a boost. So if you write it this way, all the cases are covered. And the nice thing is in the special case that you are in the rotation case, then if you work out this square root, it becomes an imaginary number, and that turns the cosh into a cosine. And the same for the sinh, it becomes a sine. And so then it becomes Euler's formula that you might have seen. So this is kind of a generalized Euler's formula that covers all three of these cases. Long story short, the bireflection has two invariants now, right? Because the only invariants under this are the scalar itself and the bivector B, because those commute with this bireflection. And B is now the eigenelement. If I give you, so for example, for a rotation in 3D, then B would be the line, the axis around which you rotate. And so that characterizes it. Once you know that line, you can reproduce it. And for trireflections, we can again play the same game. We can also split them into a commuting reflection and a bireflection. So the reflection is given actually by the vector part of the trireflection. And you can show quite straightforwardly that that commutes with the original trireflection P. And so our trireflection P can always be written as a reflection, small r, times a bireflection, capital R. And the bireflection now is a product AB, right, of two reflections itself. And we already know that a bireflection has an invariant, a bivector B, capital B. So the trireflection as a whole then has three invariants. It has the reflection, it has a bivector B, and the intersection of the reflection with the bivector. Sounds a bit abstract perhaps, but I have a picture here that shows them to you for the 3D case. So the reflection, if you have a rotoreflection, that's the combination of three different reflections. The reflection, small r here, that would be this orange reflection. The bivector is this line, the axis of the rotation. And r times b is the point where this plane and the line intersect. So those are the three invariants. And again, R and B are the eigenelements because they characterize this transformation. And that brings me to the last one. That's the quad reflection, and that's the most interesting case. Because if you take the product of 4 different reflections, so that's again our screw motion as an example, then we know that each of these bireflections can be written as an exponential function, right? So if I just put parentheses around it, I take the product AB, I know that's an exponential of some bivector B1, and I take C times D, that's the exponential of some other bivector, I call that B2. But now we have a problem because in general, the product of e to the power B1 and e to the power B2 is not the same as e to the power B1 plus B2, unless these two bivectors commute. And for a general pair of bireflections, that will not be the case. So this only happens in the special case that these things happen to be orthogonal. These two pairs of reflections happen to be orthogonal, like I've drawn it here. And yeah, if only there was a principle by which identical mirrors are always eliminated, such that we are always left with orthogonal spaces. So it turns out that that is indeed always the case. And so the challenge before us now is to actually find those commuting bivectors B1 and B2. But we know already, hopefully from the basis of the explanation I've given, that that will indeed be the case. Now this is a tough challenge, so maybe we can start doing it the other way around. So a simpler question is, if I have a general bivector, can that be split into commuting parts? So specifically, those commuting parts should all be simple bivectors, so lines in the 3D case. And simple bivectors are always of the form that are always such that they square to a scalar, and they're always the intersection of two planes. So let's start off with the simplest example, and that is I say I have a bivector B, and it's the sum of B1 and B2. And I want to find B1 and B2. And in this case, it's actually quite straightforward. If we assume commutation, we can find the answer very rapidly and then verify that it works. So the way to solve this is I start with this polynomial here. B1 minus BI, B2 minus BI is 0. Because if BI is going to be, at the moments that BI is going to be equal to either B1 or B2, then this will indeed be 0. So I want to find the roots of this, but the B's are bivectors and not normal numbers. So now I just work out the brackets. So I just multiply everything out. And I assume that these things are already commuting. So you find B1, B2 minus BI, B1 plus B2 plus BI squared. And this can be simplified by quite a bit because B1 plus B2, that's just our original B. BI squared is going to be the scalar value that I call lambda, lambda I. And B1, B2, that is actually the wedge product of B with itself, weighed properly. So actually, it ends up being this, a half B wedge B minus BIB plus lambda I. And from this, I can just solve for BI. So that's the equation we find. BI must be of this form. And I know now, I know my B. So I know almost all terms here, except the value for lambda I. And the way to get at the value for lambda I is you take the same equation again and you square it, because then, again, some of this BI here will become another lambda I if you square everything. So let's do that, and then we find this polynomial equation. It's not perhaps pretty to look at, depending on who you ask, but all of the quantities here are scalars. So this is actually a very easy equation. It just looks a bit complicated, perhaps. But each of these quantities is a scalar, so this is just a normal quadratic formula. Right, so now we're back to Charismi. We know how to solve this. So we can just solve for lambda I. If I have lambda I plug it into this formula, and then I know my B's I. So actually, that completes the solution. Again, details, if you want to be more rigorous, are in the paper. So now I can address the original problem. What are the invariant quantities of this quad reflection? So I have the product of 4 reflections, and I want to find these B1 and B2. So we know that the product of 4 reflections will always give a scalar part, a bivector part, and a quad vector part. And so essentially, to find B1 and B2, you just take the bivector part of this, and you just split it. It's a bivector, so we know how to split it now. And we know that it has to be proportional to this B1 and B2 quantity with some trig functions as coefficients. So essentially, it just boils down to decomposing this part and undoing the trig functions or just normalizing it. And so then we find that for our quad reflection, we have 4 different invariants: the scalar, B1 and B2, which are lines, and then B1, 2, which is where those lines meet. So in this particular example, my B1, one of them would be the axis of rotation, the other one would be the axis of translation, where those 2 parallel planes intersect. And B1 times B2 is a bit hard to imagine because that would live in the 4th dimension. Unfortunately, I don't have a picture of that, but it is an invariant. It's wherever those 2 lines intersect in some sense. So now I can complete this part. We know now that any quad reflection is actually generated by a bivector B, which I can split into 2 parts, a B plus and a B minus. And in the 3D PGA case, this B plus can lie anywhere in space. That's the rotation axis. And B, that should be, wait, sorry. B negative can lie anywhere in the space. So this first one should be a minus sign. So that's the rotation axis, and B plus always lies on the horizon. But in representation theory, we don't split in a part that's anywhere in the space plus a part on the horizon. We split in a part that's attached to the origin and a part that is attached to horizon, right? So we don't have any freedom here in the spatial part. And that is why, if we go back to the story of representation theory, we say, okay, I have my bivector, and I split it into the part that's attached to the origin and the part that's attached to infinity. And then I transform it in this way, and then I say, oh, this matrix cannot be decomposed. But it is because it is the wrong question to ask, because we said it's only things attached to the origin and only things on the horizon, but where's the rest of the space, right? And so that is the mistake that's made there, and that is why this matrix cannot be decomposed, whereas if we take the GA route, we can decompose it and show that the bivector can always be split into 2 lines. And this is important because this is an often used technique. In physics, we often split a Lorentz transformation into a rotation and a boost part. And in rigid body kinematics, the analogy would be you split a screw motion into a rotation and a translation part, right? So we just make this ansatz that our transformation lambda is of the form translation times rotation, or boost times rotation. And then we find those 2 parts. But the thing is, those are not the correct invariants of the transformation. And so that leads to a lot of non-intuitive phenomenon, and a notable one in physics is Wigner rotations. But that appears because this split is not the correct split to make, because you should split on the invariant quantities, because that's something that all observers can agree on. And then very quickly, we can now extend this actually to general 2K reflections. So this can always be split into commuting bireflections. And a 2K reflection is always generated by a bivector B, capital B, which can then be split into K parts, K commuting parts. And I will just post the formula here. If you're interested, you can look at the paper. But the key point is these wedges of the bivector turn out to be crucial. So you just have to take wedges until this becomes 0. Then you know the value of K, like what the highest one was. So you take these quantities Wm, and then you solve a similar formula to the one we did before. But it admittedly becomes a bit harder. And with this decomposition now, once you have a bivector B, and you split it into these commuting parts, then it becomes trivial to exponentiate. Because the exponential of some bivector now just becomes the product of these simple ones, where each of these simple ones essentially follows Euler's formula. So they're all simple. And I could also show you the counterpart of this, which is taking a logarithm. So that's going the other way, given R, find B. I will skip that now, but it is also enabled by this same idea, so we can go both ways. And lastly, something I want to point out is that a 2K reflection, so you take the bivector part, you split it into k different commuting simple bivectors. So that's this first row here, B1, B2, up to Bk. But now you can start making combinations of those, right? So you have k choose 2 pairs of these, which are again elements of geometry. So that's all the way up to the last term, and you can start combining them all the way up to the product of all of them, and that will also be an invariant. So in total, for a 2K reflection, you get 2 to the power of k invariants. And those are all valid elements of geometry. And the astute physicist might be thinking, oh, but 2 to the power k invariants in a transformation that acts on a 2k dimensional subspace. That sounds familiar to spinors, because spinors have the same 2k, but then complex dimensional degrees of freedom. And if that is a question you are indeed curious about, then again, I can highly recommend David's talk tomorrow. I just want to quickly address 2 critical questions people might have had during some of the things I said. So one thing you might have noticed is that I need an inverse to do this split, right? So to split a bivector, I had to divide by some complicated quantity. And the question might be like, do you always need that? Because then you've just shifted the problem a bit, right? Because now you need to compute an inverse, which is also hard. But that's not in general necessary. You can also get at it through the eigenvectors of this B. But I think the closed form solution is much nicer to show in a presentation and more insightful. But no, you don't need an inverse. And so far I've only talked about 2K reflections that are of the form, the exponential of a bivector. And a critical person might also say, well, not every 2K reflection is of the exponential form, which is true. But even then, you can show that it is still generated by a bivector. So really, splitting the bivector is all you need. And that is a follow-up paper that we are now working on with Steven and David Ilbode. We don't have the title yet, but that's not the most important part. The most important part is the subtitle. And we do already have that, and that will be Eigen, Ander und Ideal. And the und is there because it's meant to be pronounced in the German way, like Eigen. All right. So that brings me to the last part, which is the speaker part. So now I can briefly talk about what this could potentially yield us in the context of physics. So just as a quick recap, in the traditional everything is a vector mindset, we often think about these Euclidean groups as a semi-direct product of the rotation group and the translation group. Right, so that's SO3 and the translation group in 3D. And then you say any element of the special Euclidean group is a tuple, a pair, of a rotation and a translation vector. And then any arrow in this space transforms as RV plus T. Now, and then in order to transform the higher grade elements, we again need representation theory, as I talked about. Now, as we have seen, in 3D PGA, we got actually a much more elegant representation of these ideas that doesn't need representation anymore. One transformation can act on all the different elements. And a question you might ask is there another famous group that could benefit from a similar treatment? And there is one, and that's the Poincaré group, and that is a pseudo-Euclidean group. And it is the semi-direct product of the orthogonal group in space-time with a translation group. And then we again say that any arrow transforms under a tuple of a Lorentz transformation and a translation. That's an element of this Poincare group. In the same way, so then an arrow V transforms under lambda V plus T. And again, we need representation theory to work with all the higher grade elements. So that sounds very familiar, and could the PGA mindset give us some advantages here as well? So again, I will start with the 3D algebra now. That was the biggest one we have. And now I need to somehow introduce time. So I will play the same game again, like, oh, I was looking at this space, but actually it turns out that the planes I was looking at this whole time were really not planes, they were volumes. It was just intersecting my eye the wrong way. So you have that, but you also have the volume itself, and that will remain a volume once you rotate in one extra dimension. So what was planes, what looked to be planes, are going to be volumes, but the volume I could already see will stay a volume. And so I will use an extra basis vector again, E4, to move the volume up to the level of the vectors. So then you get this algebra, 3, 1, 1. And now I have 3 basis vectors squaring to a positive number, 1 squaring to a negative number. And those are volumes. And now again I can start intersecting volumes, 2 intersect into a plane, 3 intersect into a line, and 4 intersect into an event. The nice thing, by the way, about all these elements that we get here now is when you intersect them, when you intersect the spatial parts, you would still get normal rotations. If you intersect 2 parallel, or if you do 2 parallel reflections, you would still get a translation. And you now get this extra thing called a boost, where you mix a dimension of space with a dimension of time. Now, a weird question, or obvious perhaps question you might ask is, why does E4 suddenly have to square to -1? Because we didn't do that before. Well, because it has to. Like, otherwise I wouldn't get space-time. But I cannot give a geometrically tangible answer for why suddenly the square changed compared to the other times I did this. And another question is, why did I choose 3, 1 and not 1, 3? Because in physics that's a common debate. Just the principle of least surprise for this talk, otherwise all my pictures and my colors here would have to change. But really there's no good reason for that. Again, it's probably better actually to do the other one, but everybody's free to choose what they want in that regard. So now we get something nice. We get, for example, that all events are created equal. So any event is the origin plus an amount in the time direction, space, and the different space directions. And so all points are now defined in a homogeneous way. They always have the same square. And the origin is this quantity E1, 2, 3, 4. I have some points at infinity, which are the normal points in those directions. And then I have finally a point at eternity, which is the point to which we're moving in time. And now we can consider something nice. I have a particle at rest at the origin, and it is just sitting there at rest, so it moves towards the point at eternity, right? So the point at eternity is E0, 1, 2, 3. And now I can just join those 2 points together, the origin with the point at eternity. My time direction is upwards. And so now I join those 2 together and I make a line E1, 2, 3. And that is the line along which, the world line along which a particle at rest would move. And so, for example, if I want to talk about a particle now with a mass of m, then in its rest frame, it would move only in the time direction. And so it is represented by this trivector P, which is equal to m times E1, 2, 3. And it squares to negative the mass squared, as we expect. And now this is something that I'm sure Leo will talk about more, the inertial duality. So if I now take the inertial dual map from this momentum line, then you see the symmetry here in this picture, that these momentum generators, or elements, sorry, are dual to the different bivectors. So if I now dualize from E123 here, then I get E40. And if you think about it, so that is the element that generates a translation towards eternity, right? That's my new dimension. That moves me up in space. Up in time. So that's really neat that we get that duality. And now I can ask a question. Which elements do I still have that leave this momentum line invariant? What still commutes with it, in other words? And this is something we technically call the Wigner-Little groups. So the Wigner-Little groups are the invariance groups of a momentum line Pm. And this is exactly the kind of question we had the invariant decomposition for, right? That is exactly the thing that helps us find the commuting subspaces. So if I just do it for this specific particle at rest, where I know exactly that it is proportional to E123, which elements can I find that leave this invariant, or that commute with it, in other words? So those are these three elements, E014, 024, and 034. But if you take that dual, something interesting happens. Those are E23, E31, and E12, and those are just the generators of a rotation. So indeed, around this momentum line, there's still the invariance of rotation, under rotation. And those are the generators of the spin-free group, which is isomorphic to SU2. And to a physicist, if you hear SU2, you instantly think spin, the quantum property of spin. And so the question is, can I generalize this idea? So if I take now a general pseudo-bivector, P, not for a particle at rest, any one, then I can now always split it with the invariant decomposition into two commuting parts, the massive part and the spin part. So the subscript m here refers to the fact that this part squares to the negative of the mass squared. And it turns out that this PS part, because it's ideal, it lies at the horizon, that always squares to 0. Just like it does, in a sense, in the 3D case. So if I now want to find out what the behavior of this PS is, I do one simple thing. I take PM outside of the brackets. So I'm left with 1 plus PS over PM. And then I have to explore what is this new quantity PS over PM. So I call that S, capital S. And if you investigate, it turns out that's a pure direction. So it's a direction somewhere, pointing somewhere towards space and time at the infinity. And so it has only 4 components. So I can index it with S mu, E mu times the pseudoscalar. So it has only 4 components, not 5 like you might expect. And this quantity S is such that it always commutes with PM. So this S mu is the spin 4 vector. That's the classical terminology for it. And now I can just find PS, if I take its dual, that will be the generators of these Wigner-Little groups. So if you have, for example, a time-like momentum, like we all are right now, that's the normal case, then you have a spin 3 as an invariance group. So that's isomorphic to SU2 for spin. If you have a light-like trajectory, so like light does, then you find that this invariance group is SE2. And if you have a space-like particle, which are these hypothetical particles called tachyons, then you would find spin 2, 1. And that all follows very nicely from studying these different invariance groups. So those actually, if you just classify this, you find the same results that we traditionally find, but now from the invariant decomposition. And I should stress, by the way, like I'm not making any claims about quantum mechanics. The analysis I'm doing is just purely classical. But I just want to say that these degrees of freedom are clearly present in our algebra. So we're almost there now. Now we get to something called the unified Lorentz force law. And that is the idea that for any k factor x, if you want to see how it updates under electromagnetic fields, so the electromagnetic fields are F, then it always goes via commutation. So the derivative of x is always the commutator product of F with x. And in STOP, our space-time algebra, momenta bylines can always be split into these two commuting parts, as I've shown. And we know that ordinarily for particles, the force velocity is updated under electromagnetic field by something called the Lorentz force law. And the spin is updated by something called the BMT equations. And normally those are two separate problems, and they're treated separately. But maybe our momentum byline has both of those unified, and indeed it does. So actually there's one single unified Lorentz force law that covers both the velocity part and the spin part at the same time in the classical limit. So where the G constant is 2 and assuming homogeneous field. So that's in the simplest case. But again, I'm not making claims about quantum mechanics. Those are still left to explore. But it's really exciting that the degrees of freedom are already present in this algebra. Okay, that brings me to the conclusions. So starting from some geometrical principles, we first found the pseudo-Euclidean geometry, and that it is captured by Clifford algebras, specifically by the PGAs. And elements of geometry are the invariance of transformations, hence the title Hiding in the Fold. They were hiding in the fold line of the transformations this whole time. And the elements of geometry are also themselves transformations, right? They are interchangeable. And both are represented by K reflections. And we can compose different K reflections with the product, but we've also seen that to act with them, to actually perform a transformation, you use this two-sided product. So X goes to Rx, R inverse. So that's all just the composition of these K reflections under the geometric gauges, with the geometric gauges taking care of the rest. And we've seen that the higher grade K reflections do not give us anything new actually, right? So think do, re, do. There's nothing after re. So nothing after the bireflections. And I hope to have also given a nice preview of how this mindset also has potential for physics, because the geometrical invariants are something that all observers can agree on. And that's a key feature that we like in physics. And the inclusion of the elements at eternity and infinity has also led to a previously unknown unification of the Lorentz force law that includes the spin degrees of freedom. So thank you for your attention.
Martin, thank you for the tremendous talk. I think you know Omer.
I know and love it, yes. Okay. Thank you.
Maybe questions?
Yeah, does anybody want to do some questions? All right, so we have a small bonus talk that was planned very last minute, actually only the beginning of this week. And it'll be given by Eelco, called Catching Geometric Waves. And it's about, he's the author of the NumGA GA library, which allows you to do very easily I should say, geometric calculus. And so we'll be looking at some interesting relativistic wave equations with some very fancy pictures.
Let's see. Am I audible? Great. Thank you very much, Stephen. Yeah, so I'm going to be talking about relativistic wave equations of any grade and dimension. Got a little QR code here on the screen, which you can scan with your phone if you want to have a runnable example on your phone as you're watching the stream. And I've put that on a separate slide actually as well, because I heard that maybe for the people watching the stream there might be a bit of a thing on top of that. So I'm going to leave that there for a few seconds for the people that want to get it. Let's see, you still see some phones there. If all the phones are gone, then I'm going to continue. Yeah, so what's this about, right? One of my motivations in this is that I've, for a very long time, always wanted to create a game called Quantum Pong, where you take a wave particle and you do something fun with it for educational purposes, right? Here on the screen you see an animation of a wave packet, and you could try and think of all kinds of interesting game mechanics for that. Make it solve a maze, or just do literal Pong with it, or something of that nature. But if you're playing around with that, of course the question comes up like, how do you simulate a relativistic electron wave anyway? And there's a bit of a bleak picture here, right? I did applied math and I've done all the classical wave equations, and there's lots of stuff out there and it works really well. Then you have the Schrödinger equation, which is already not as great. The methods are all kind of finicky. And then I've often tried to find, okay, but how do the real physicists do it that want to do the real electron wave function? And it's kind of, as far as I can tell, there's just really not much out there at all that I could comprehend in any case. So if it comes to sort of the more general question of multi-vector valued relativistic waves, it seems perhaps like a pretty hopeless thing. But one of the things, this is perhaps a slightly more bleak picture than it really is, because there is one relativistic multi-vector valued wave equation that actually has a discretization method that works really well. This is the Yee scheme for electromagnetic waves, and it's been invented in the 60s. People still use this today because it's a really elegant scheme in a way, and it just works really well. So I thought, let's rewrite this in a more geometric way, because the electromagnetic wave equation is fundamentally quite a geometric thing, although this particular way of looking at it doesn't make it very apparent, I would say. And this is kind of a schematic representation of what the inspiration behind the Yee scheme is. And the classical Yee scheme kind of encourages you to think of magnetic fluxes on faces and electric fields on lines, which is kind of the wrong picture. If you really want to look at it geometrically, you have to think of the electric field as also a bivector swept out in time. And well, why do we want to look at this? Because if you look at the math behind this, then the Maxwell equation and the Dirac equation, the differential operator is actually kind of the same thing. And some people call this thing the vector derivative. I really like to prepend geometric before that, because it's a very geometric thing. And there's also the exterior derivative, which is also a vector derivative, and that's not what we're talking about. So geometric vector derivative, but what is this thing anyway, right? It sounds complicated. Maybe it's not really going to help us at all. But when I first learned about this concept, I was kind of amazed by how simple it actually can be, I think. So I've made a little animation of how one way of thinking about the discrete geometric vector derivative. And here on the right, we have a n-cube grid, as we call it, a grid of cubes, in this case, two-dimensional one in x and t, because that's the biggest one we can plot on our screen. In the middle, we have a geometric product, and then on the left, we have all the vectors in our algebra. And if you write out that product between these things, make a little animation, then you're generating effectively this set of equations, whereby, we're looking here, in this case, at a one vector valued field, so only the lines, we're ignoring the points and the faces for now as our field. But yeah, if we write out all these multiplications, and you have to think of this as kind of a convolutional operator going over the entire grid, you can kind of summarize that in this type of equation below. Okay, does that help us? Well, we're going to try and turn that into code. And that only takes a few lines. So let's see, we have here basically, is it visible? I think I wanted to zoom this in a tiny bit. Is it decently readable like this? Okay, then I'm not going to bother figuring out the zooming again. All right, so we basically have the same structure of equation that I just shown on the screen. We have an interior derivative of t with respect to t, and an interior derivative with respect to x of x, and they're both things of grade s or scalars, and so on, exterior derivatives for t and x and t. And these are very simple operators, so these are just simple upwind and downwind finite difference operators, nothing more to them, and this whole EDT thing is just an in-place array update. And then if we run that, there's a little bit of boilerplate below to do the plotting, but then that's not very interesting. So we get something like this. We initialized it with a, excuse me, how do I drag stuff here? There we go. I'm using someone else's laptop, excuse me if it's all a bit clunky. We set it up with an exponential of a quadratic in the middle, so an impulse response in the middle, and we let this thing run, and what we see is like two wave packets moving in x and t across this xt diagram, and it's a periodic boundary condition, so it goes around and it just will keep going around like that forever. And it's important to appreciate that this code doesn't just look like the math. In fact, this code is an exact realization of the geometric relationships we generated by performing this discrete geometric product. There's no approximation. This is an exact realization of the mathematical principle. If you look at this thing here on my screen, if you take the geometric product with the one vectors, you're going to get 0 everywhere. So that's kind of a cool thing about all of this, I believe. And we can do this not just with this xt space. We can do this in all kinds of dimensions, and I've kind of hidden these operators behind this little helper method to make things a little bit cleaner, sprinkled on a slight little bit of syntactic sugar, so the brackets are nicer. But it's basically the same thing. We have here the geometric vector derivative of phi, where phi are the bivectors of sort of your classical space-time, if you will. What we get out of that is this block of equations with interior derivative terms and exterior derivative terms and interior derivative terms. So we have here all the terms of grade x, y, t, and then we have the exterior derivative with respect to x of yt, and then minus y xt, because we got to reorder them and do one swap to get it in the canonical order. So these terms are just all the terms that are in the geometric product of these differential operators and the field. And if we run that, again, we're not really doing anything here except for recasting a 60-year-old algorithm into geometric wine bottles or whatever. We get a wave or a slice through a 3D volume. We've got here, you see the periodicity in Z, waves coming around. All looks nice and colorful. And we're doing the same thing, right? We got a little impulse response of a Gaussian blob. What else? And what are we really looking at? These colors are the first three components of phi. So that's the spatial bivector components. So that's, in this case, the components of the magnetic field. So that's what we're looking at. Looks nice. I think I want to go back to the presentation here for a second. So yeah, so we, like, without any proof or anything, I'm just going to state here sort of the general principle that this works for all grades and metrics. Yes, exactly. So, well, boring, blah, blah, we form the product. Well, the important part is you can always form this split between having a slice of time-like variables and a slice of space-like variables. And given these, you can find this one, and you can find this one, and you can find this one. And it never involves any approximation. And this is very much due to the geometric product if you go into the details of why it all works out. Because of the geometric product structure, you always have this leapfrog structure that allows you to have this causality, whereby if you know one slice in time, you can, all the other ones in time are implied as you march through time. So here we have this guy again on my slides. But now we want to go back to the code. So of course, if you're looking at this, you're saying, hey, we have this thing here, geometric looking, 6 bivector components. I'm claiming it works for all grades and whatnot. We were kind of interested in the even grade algebra as well, so let's go there. Let's write this out for the even grade algebra. And it actually looks kind of simpler in a way, you might say, than the bivectors. We've kind of filled out the whole grid of numbers, but we're not doing anything different. It's very much the same code, and if we run that, it doesn't look that spectacularly different from the bivector equation. We got a wave traveling at the speed of light around a light cone. Colors are slightly different, but it's non-trivial that it works in the first place, right? It's not exploding. We got beautiful colors, so something going on here. But let's move on from that. Let's do something different, or actually something that's kind of the same. Using the same algebra here, 3 spatial dimensions, 1 time dimension. Just renamed the Z to W, so that doesn't change anything. Still talking about the even grade subalgebra here, 8 components. The reason I've renamed it to W is because before we had a cube of 64 by 64 by 64. Now I've just squashed it down. I've squashed down the Z dimension to make it a very small dimension. And that might sound kind of, not interesting. But if we run that, and I should run it first and then start talking, I think. I don't want that. If we run that, you can see it looks qualitatively quite different. And if you were paying attention, it seems as if these things are actually not moving along the light cone. It seems that they're moving slower than the speed of light, actually. Which in a sense they aren't, but we'll get back to that. But in any case, it's already pretty cool looking. If you were looking for fancy animation in your game, something to look sciencey and quantum-y, and you want to create a texture on your wall, then it was already this would already be pretty useful, right? And there's another thing we can do. So let's see, comment. So before I kind of shrunk down the whole thing flat, but now I've given a bit of a spatial profile, if you will, to the squeezing of the space. And essentially, I've relaxed the restriction that we were convolving all these unit length vectors across our grid, but we're using a slightly different length vector for W in every location. And if we do that, we get something that is quite strikingly different, right? We have a really confined wave packet, if you will, which is perhaps to some physicists very obvious. If Kaluza and Klein might have something to say about this, but we're not going to go there. We can direct the wave by manipulating the shape of the length of the vectors of W. And there's more we can do with that, because I have this default initial condition here, but if we switch over to another initial condition, so this one was where I had an impulse applied to the field at the center of the potential of this quadratic that I made. Now I've offset the quadratic and the impulse a little bit, and then you get stuff like this, right? It's sort of a classical, well, not a classical, but, well, depending on your interpretation of the word classical, particle trapped in a well, in a potential well, right? Except this is not the Schrödinger equation, right? We're looking here at an equation with what is it, 8 field components that are all actively participating in whatever it is that you want to believe this thing to be. In any case, again, it's excellent material for making cool animations with, for starters, right? So let's try something completely different. Moving on, so let's try a 2D equation for a change. And to spice things up, I'm going to make this the full algebra, so all the elements of the algebra of x, y, t. And to make it even more interesting, because, Schrödinger and Dirac, they both also did something like this. There's not just a first order derivative, second order derivative, but there's also term somehow proportional to phi. Let's also throw that in there and see what that does, right? And let's see, no problems here. Looks remarkably similar, right? And wait, did I even run the right file? Yeah, it does really look remarkably similar. And that's kind of interesting, I find. There's not just a superficial similarity. As a matter of fact, if you have a field with the minimum amount of non-trivial dimensions in W, which is 2, you can decompose the field into a component that doesn't vary over W, which I call here light-like, which is, you know, a +1 constant in W, and the rest that's left over is sort of anti-symmetric in W. And if you think about what the derivatives of these things with respect to W are, then the light-like part does not travel along the W at all, so the W is irrelevant for the light-like stuff. And the massive stuff sort of maximally travels around that compact dimension. And you also have the result that those derivatives are proportional to the thing itself. So if you look at the structure of these equations of the even-grade algebra in the 1-up space, the W plus x plus t plus, versus the geometric vector derivative plus a zero order term over the full algebra, and you see that this last column, the derivatives with respect to W, are actually proportional to these multiplications by m, which is phi itself, right? And then, of course, if the derivatives to zero with respect to W are 0, then you get this, which is just the thing without the W. So I thought that's an interesting result, personally. And let's go back to the code to look at some more examples. So I said any dimension, any signature, no, not any signature, by the way. So we want to go higher, right? 5-dimensional. So we have a regular x, y, z, and t, plus an extra compact dimension W, 5-dimensional. If you write this out, it looks like this. It worked the first time when I tried this, or it worked the first time after I wrote a little code generator to write this expression for me, but we still have the same thing, right? We have everything that does not have t updated in terms of everything that does have t, and everything that does have t dependent on everything that does not have t. The structure still works out in the same way. What does that look like? Let's turn this back to true. Well, first of all, I said I was going to run them first and then talk about it. Sorry about that. Click, click. What? Click, click. Interesting. Okay. I am not at all sure what happens here. Excuse me, live demos indeed. Seems like it's just ignoring my run command somehow. Maybe I should. Oh wait, I still have a figure open, that's the issue here. Sorry about that. It just went into the background because I clicked once too many, and now I've clicked 500 times and maybe it's gonna be even worse. Well, okay. Well, there we go. I don't know what this is, but it also looks cool, and it works. It does not explode. You get a sense of something rotating around the vertical axis here, right? And this, by the way, is also in a potential in W, right? So it's trapped inside of a potential in W. Yeah, just the fact that it works at all is to me kind of an interesting. Oh yeah, there we go. Oh God. Let's see, can I interrupt this? Because I clicked like 10 times, I think. Okay, let's just bear with this for a few minutes, rather than deal with whatever problems might arise if I completely restart everything. Yep. I think we're almost there. Okay, so yeah, let's switch this around. Try a different initial condition, just for curiosity's sake. And if you look at this one, it's like kind of less visually spectacular, but you know, if you happen to know any quantum chemistry, you might think, hey, this does look a lot like a superposition of S and P modes of an electron wave, right? So, which raises kind of the question, in this higher dimensional space, is there actually a functional model of an electron hiding in there? And that's, well, probably a question you could debate for a long time, and I don't profess to have an answer to it. I think, based on sort of my mathematical understanding of things, I would say this isn't, this equation what we have is not actually what Heston has said, so I think there's meaningful mathematical differences there. But yeah, make of that as you will. At the very least, you can make pretty looking things with it, right? And again, this is just the geometric vector derivative is 0 with a compact dimension to give us sort of the mass-like behavior. For contrast, it's also kind of interesting to, so let's take the same algebra, but now just the bivectors, we get a somehow not as nice looking equation, which is sort of less symmetrical, but it does work, but you can't really get this thing to very much look like an electron wave, right? It does seem like there's something essential about the even subalgebra in terms of getting it to behave all electron-like, if you will. Well, maybe a smarter person than me can find an initial condition here that does look like an S or a P wave, but I haven't been able to. Let's see, I think good time for a switch back to the presentation. No, not, more code. Okay, something different to talk about, kind of illustrate the idea, the difference between a light-like and a massive wave, right? So what we've got here is W, X, Y, T. So two non-compact dimensions and a W, so we can do mass, if you will. But we're actually not really gonna do anything interesting with the mass. We're gonna just give it a constant value. So there's no variations in W. I said I was gonna run it first. Let's take my own advice. So we have a massive wave, and this one is also kind of a trapped mode of a wave, but it's not trapped by potential formed in a distortion of W. We've done something else here. We've applied a little dimple to the length of the vectors X, Y, and T. And to be precise, what we're saying, like here in the middle is the maximum distortion, and the length of the vectors T here is 1/2 the length of the vectors far away from the dimple. So you might say, popularly speaking, that clocks here in the middle will run at half the speed as they would run outside of there, and that has an effect on the wave function, and it traps the wave function. And this is a pretty extreme time dilation, if you will. This like a slowing down of time by a factor 1/2. That's sort of associated with the density of the surface of a neutron star or something, so you can't really fault this massive particle to not escape from there. And this is not very theoretical, right? We know this happens. This is physics that you can measure by shooting a satellite into the sky. Gravitational time dilation exists, if you want to call it that. But now what's interesting, instead of focusing on the massive part of this equation, we can sort of say, well, get rid of the massive part and let's look what the light-like part does in the same setup. And, well, what do you expect? You start a little blip inside of this potential well, and it's slowed down a bit, and you see the wave redshifting, getting longer as it goes out of the potential well, but it gets out of there eventually, and then we got our periodic boundary conditions, and it falls back in again, all kind of as expected. But now, it's kind of fun to see what happens if we take two neutron stars. We halve the speed of time again. I'm not sure if that's, the math there is entirely right, but it doesn't matter. We slow down time by a factor 4. And now what happens to our light waves that start out in the middle of all this? They're slower in the first place, of course, so we're gonna have to exercise a little bit more patience. But they're moving outward, right? Because they're not really gonna turn around. That's not what light waves do, except that, well, you know, if you were an observer sitting somewhere here, and you were trying to detect something happening there, you're gonna get pretty bored, it seems like, right? So what seems to be happening is that the light kind of prefers to orbit around this thing that we've created instead of going out of there, which you know, is an interesting dynamic, let's put it that way. And what I found especially interesting, if we take a one-dimensional setup with the same distortion applied to it, and I'm bringing all of this up just as an illustration of why I think it's interesting to play with these visual results, not because I'm trying to make any profound points about gravity or what it is or isn't, but if you look at this in one dimension, then this doesn't happen, right? So you can't have something orbiting the black hole in one dimension. So in one dimension, it doesn't matter how big you make the distortion, unless you make it infinitely big and you slow it down to 0 in the center. It's just gonna happily, you know, go in and out the other way again. But in 2 or more dimensions, things play out a little bit differently, which is quite interesting, despite the fact that there's no singularities in this simulation, right? And it's something that I had never thought about in this way, that I'd always thought that the essence of a black hole was the singularity, but actually to trap light, you don't need a singularity, which is something that I had never thought of. So yeah, that's the main results. I'm already sort of at my summary. So yeah, indeed, the Yi scheme can be generalized to geometric vector derivatives of fields of arbitrary grades and dimensions. We can use that to simulate both light-like and massive type of waves, if you will. And all we really need for that is a geometric derivative of phi is 0. We don't even, per se, have to get fancy and add extra terms to the equation, which I thought is kind of beautiful. And we only really need a small handful of lines of code to implement all of this. And I think more importantly, really, is it's not just that it's a few lines of code, but it's also a very, very small self-contained set of conceptual complexity, if you will, right? Let's say I have kids, and let's say that one day they're at the age to have the talk, and they say, "Dad, can we talk about partial differential equations?" I would tell them, "Look, have you done your geometric algebra prerequisites? You know what a geometric product is?" And they might say yes, and then I would say, "Well, it's pretty easy. You take a bunch of one vectors, you multiply them with your field, end of class, right? Done." And you know, they're kids, so they might complain, and they might say things like, "But Dad, I don't care about like light-like or massive waves. It's not my thing. All the kids at school talking about diffusing the heat equation. When are we going to talk about that?" And you know, at this point, I would have to be strict and say, "Look, if you want to talk about exotic things like equations with derivative of mixed grades and all the complications that brings, first show me you can just multiply with a one vector, and then we'll talk, right?" I think that's the fair way of looking at things. But there's a lot of open questions about this work. So the relationship to any particular field of physical modeling, I'm not very qualified to speak on. And there's a lot of interesting questions you can ask about what other type of zero-order terms you can include in these equations, or what about interactions between fields, and so on. And to be honest, it also hasn't really brought me any closer to coming up with an interesting gameplay mechanic for quantum Pong, because that's really got a lot more to do with aforementioned interactions and how to deal with wave function collapse and the fact that these things just keep spreading all the time and making it hard to actually make a well-defined game out of. But yeah, it's been an interesting learning experience for me that I've learned a lot from. I don't know how I'm doing time-wise. I imagine, all right, yeah, I'm doing fine time-wise. So I have a bonus equation, can dig a little bit into that. So for instance, when I'm talking about different right-hand sides, right, different mass terms, if you will, if you have geometric derivative of phi, the geometric derivative toggles between even and odd grade. So if phi is even grade, then the geometric derivative of that is going to be odd grade. So I can't equate it to m phi. I need the full algebra to even make sense of that equation, right? Otherwise, it just trivializes if I have odd grade on one side of the equation and even grade on the other side. So if you insist on just doing an even subalgebra, and you don't want additional dimensions, but you do want a mass term, you have to have some kind of grade toggling term here. For instance, that could be multiplication by the spatial pseudoscalar, so that will also take phi to the odd grade, right? And you can try various things of that nature, and I've experimented with a lot of them, but they're not really part of the main talk because I can't say I understand and appreciate it all extremely well. But sometimes it works, right? For some signatures and some dimensions and some types of dualizations, it works, but very often becomes unstable and explodes. And that's something that never actually happens with the pure geometric equation, because it's really just a conservation principle, right? You're just bouncing multivectorial amplitudes around inside of the n-cube, and you're never actually creating or destroying anything, whereas with an equation like this, it's much harder to prove that the thing even makes sense in the first place. But this one seems stable somehow, and also kind of quirky in many ways. But one of the things that is kind of not so nice about all of this is that we have to interpolate our field values. I don't know if I want to explain this, but yeah. Well, let's quickly go back to the slide. You have to do an interpolation step, because if you look at this picture, if you are forming an equation over the blue square and you've got all the things that sort of extrude under the wedge product onto the blue square, we're equating those things together. That works, and then if we add sort of an m phi to it, then we can say, oh well, that's fine. We just, in our update rule from the t at the bottom to the t at the top, we include a difference over the x's here on the sides, and we throw just a contribution in there from the bivector that we're stepping over, and that works out very elegantly. If you start multiplying with additional basis vectors, say you multiply with x to get a contribution from t, then the question sort of becomes what t, right? If I want to step from here to here and include not only the difference over t, but also something proportional to t, which one am I going to grab? Am I going to grab this one or am I going to grab that one? Well, neither is a great answer, so the sort of natural solution is to say, well, you know what, we're going to average this thing, and then we could add it to that thing, but it's not as mathematically elegant, and also it doesn't always work fantastically well. Here's another one that's just in here because it's kind of beautiful if you want to see a non-trivial quaternionic equation with 4 components. I always kind of like the look of this one as well. So this is again a XT diagram of a particle trapped in a well. Yeah, and that, wait, did I go out of full screen here? I did. Let's go back. Yeah, that's the end of my talk. And if you're looking for a good geometric algebra library in Python, NumGI, I can recommend it. Also, there's an early write-up of this code and an attempt of me of writing this down on paper, which is very much incomplete, here at this link. And that concludes my talk. Thank you for your attention.
That's very interesting, but just reacting to what you said near the beginning about more or less complete absence of simulations of electron wave packets and so on. Where particles are going and where they're moving and so on, but that's just a matter of interpretation. The basic simulations are, doing what you're talking about there. So there are some which exist out there.
All right, was it also a geometric algebraic inspired work?
Yes. It was all done absolutely within GA, yep.
Okay, cool. I'd love to see take a look at that.
Those were also very pretty animations.
Ah.
Oh, sorry.
Thanks. I don't suppose you could go back to the animation? The previous slide.
This one?
No, the one with the grid showing the arrows and the simulation. Yeah, that exact one. I don't suppose you could say a little bit more about what's going on here?
Right. Yeah, I can pause this a little bit longer. So, and yeah, if I have few more seconds to talk about this, there's a little detail I want to get into. So, right, if you're smart, you might say, well, look at this thing here. Mm-hmm. This sums to 0, so let me save you the time. The product of 0 with 0 is 0. Mm-hmm. But that's not how that's not how we're going to look at it if you want to follow me along here in my story, right? So even though you might say, well, this is a thing xt, and this is a thing xt, and if this is -1 and this is +1, I just translate the vectors and I add them up and they cancel out. Well, that's not what we're going to be doing if we're trying to do field theory, right? We would offend Albert Einstein if that's what we did. So what we're sort of saying in the context of field theory is that we can only sum things together if they're both of the same grade and they're also in the same location, right? So if we look at sort of an edge here in the middle, then the thing extruded to the left and the thing extruded to the right, you might sort of argue that, well, that's 0, but we're going to say no, the thing extruded to the left is in this bucket and this thing extruded to the right is in that bucket. And if you look at it that way, then you get the difference equation, let's say. If you don't, you don't. I mean, this is math. You're free to do whatever you please, but that's an important subtlety there. And yeah, let's see, what else can I say about it? Maybe just play it once more, right? I'm just working out here for a single vertex, right, how it gets contributions from all the products of the 1 elements in this grid with all these vectors on the left, right? So, and it's a geometric product, so you might say, hey, this x times this thing that was on the screen a second ago. Let's see. So this thing, well, it has a vanishing wedge part, right? So we're only it only has an inner product contribution. As it collapses onto the vertex, and the wedge part doesn't matter. And likewise, if you are multiplying an element that already has t in it, like this xt, and you multiply it by t, it collapses onto the x here at the bottom.
Okay, so the arrows going towards the the blue point in the middle are the points around it affecting it.
Right, yeah, so there's a relationship, we're stating a relationship between these four edges as they relate onto the vertex, let's say, right? So if we know the past t and we know the current x, then by that relationship we exactly imply the value of the future t, let's say. And that simple sort of causal structure is respected everywhere in all these product terms that you form, regardless of the grade of the cube that you're looking at.
And I notice you have a minus t, that seems the opposite of causal, so something being affected by something that's after it? Or?
Well, in a finite difference sense, I suppose it is, right? We are relating stuff in between different time slices, if you will, so...
Okay.
Yeah.
Thank you.
But there's different ways in which you can derive this. I just think this is a particularly... I just really wanted to point out the geometric product structure of what it is that we're really doing here, and how you want to think about how to discretize or whatnot. That's, well, you can look at this in a lot of different ways, but...
All right. Okay. Thank you again. Ilko, I hope you like the local brew.
I do.
You're also invited to the newsroom for
Yes.
one-to-one questions.
All right.
wou je het volume testen? Ik ben te horen, zo te horen.
Okay, so welcome back everyone. The next speaker is Dr. Leo Dorst from the University of Amsterdam, who is the author of Geometric Algebra for Computer Science. And we've been working closely together for the past few years now, and he will be talking about geometric dynamics, which is basically classical mechanics in PGA.
Yeah, thank you, Steven. We've been working closely together and also working closely separately, I think. But yeah, so I also put Steven's name on this talk because it is based on stuff that we've done together, and all the demos that you will see are programmed by him. This is not totally original work, I would say. The original work at the basis of this was done by Charles Gunn. Steven was somebody who tried to decipher his thesis by programming it out, and then I tried to write it down in a way that I could understand it, and that this is the reflection of that. So you've seen a little bit about the geometric algebra, you've seen a bit about notably the PGA, which is supposedly a good algebra to describe Euclidean motions in 3D space. But well, there's more. If you really want to do motions, then you would also like to do motions of heavy objects, not just of these ephemeral lines and planes that are infinitely thin, points that don't weigh anything like that. And we know how to do that. There's Newtonian classical mechanics that used to be described by vectors. Does PGA give another way of talking about that? Well, it does. And this talk will show you how we could get a coordinate-free geometrical representation of the things that we're interested in. That the linear things of sliding and the angular aspects of turning will be unified in a way that works both for the objects and the motions. So we're not going to develop a separate motion representation and a separate object representation and somehow say, oh, if you want to go to motions, you have to go to this weird space of quaternions. No, you can divide two lines and get the motion that turns one line into another. We will show by Steven's software that it's very easy to integrate the resulting equations numerically, but we'll also show that the vector methods are contained in there, and you can very easily, if you're used to doing these things by vectors, embed that, upgrade it, and get all the symmetries and advantages of the PGA. There is some historical provenance in doing it this way, the screw theory and the spatial vectors. I'll relate a little bit to those at the end, but it's more easily developed from scratch just in the PGA context, and then we'll do the correspondence later. It's not that hard, so an hour is enough. Okay. I first want to show you a little demo. And that should be contained here. Oh, sorry, the merchandise. It's always me. So here you see an implementation by Steven of something that we should be able to do at the end of this talk. So I can drag points around. There are springs there. There's clearly a mass that has some heaviness. There is a gravity that tends to pull it down. And when I twist these things around, the motions are made by the Newtonian mechanics that these things obey. And the code that belongs to that is rather compact. There is a little bit to generate the block, which is up here. You have to describe something about the inertia. You have to include the forces. We have gravity, damping. We have the hook spring, both hook springs. This is the equation of motion. This is the integrator, and that is the picture. That's how simple mechanics is. And we do that by encoding that in an efficient way using the primitives of PGA. I'll go back to the full screen. Give many a shock. So what we're going to do, I give first a preview of what will be the outcome so that it gives you a bit of focus. What we'll be able to do is do everything in terms of bivectors, dual bivectors, describing how an object moves, what its body properties are. And there will be something about momentum and forces, of course, because that is what's going to cause the motion. And this will be the full framework that we're going to use for that. So these red letters are the PGA thing. We will be able to make correspondence to how things are done classically, and there's several things to notice. Angular and linear momentum in the blue is the classical way of encoding it, with an angular momentum vector and a linear momentum vector. Forces and torques are separate. Somehow they interact when things happen. And there's a few things to observe there. So rotation and translation are apparently in the red side completely unified, classically not. We do recognize all the classical things, but in classical things you have to be very careful where you are when you do it. If you have a force that is acting here and you go and stand here, then there will be an extra torque, and you somehow have to compute it by formulas like this, and you have to remember that you have to compute it because it's not automatic. Whereas in geometric algebra, you see that somehow this force that I have here, there's an equal sign here and there's another equal sign here. This is exactly the same algebraic object that describes a force relative to a point R or relative to the origin when it requires a torque. This is going to be a very unusual property of the system that we could call coordinate freeness. It doesn't matter where you are. The object remains exactly the same algebraic object. You choose later, okay, if you want to stand here, you want to know what the force and torque are, you can compute that, but the element remains the same. And that is true for all the aspects. So it's truly geometrical in that sense. And the trick to do that is to go to bivectors and dual bivectors. We are going to have to make a distinction between those two. So the agenda of the talk is I'll talk a little bit about the geometric primitives, so the how to make elements of geometry. Much of that you've already seen, but we'll just do it again, but faster. Then I want to describe about how to characterize motions by bivectors, because that's going to be central. This differential equation that we're going to set up is at the bivector level. We'll then talk about Newtonian motion, so how to give objects mass and what the consequences of that are. And at the very end, I will show how you can take your classical system, make it into PGA, and have all the advantages of this unified approach. Geometric primitives. We have seen this several times already, that we're going to work in 3D PGA. That's the plane-based geometric algebra. We know that for 3D that is four-dimensional because the basic vectors act as the reflection operators, and you can do 4 reflections before you get saturated and in three-dimensional space in planes. And then when we represent a plane in that space, we use a normal vector and we use a distance to some kind of an origin, which is very, very similar to how you do it in homogeneous coordinates, where you also put a normal vector. You have to make a 4x1 vector with the normal vector here and minus d over there to describe the linear equation. And the special thing about PGA was that there was this one weird vector that squares to 0 to make it Euclidean geometry. When you do that, you get something that is actually for sale. It is the coffee table, or the table on a coffee mug, of all the elements that are in the PGA. So this is a three-dimensional geometric algebra. The planes are the vectors. If we meet 2 planes, we get the lines, so they're of grade 2. If we meet 3 planes, we get a point, so they're over here. If we look at the planes used as a reflector, we are here, and the point reflectors are over there. If we use the lines to do our motions, then if it's a finite line, we get a rotation operator. If it's a line at infinity, we get a translation operator. And if we combine all those, we get the motors, which are, they've been called rotors in general, or versors. We'll call them motors when we talk about this algebra. And you see that lines are represented by 6 coordinates, very much like the Plücker coordinates. We will see that they'll form screws to describe motions, which is very much like a Lie algebra of the motion. This is the regular homogeneous coordinates at the point-based level. This is how you do normal equations. And we'll also see that the quaternions and the dual quaternions are in there. And the nice thing about this is that you see both objects and operators unified in a single framework. Nothing is unused, and the relationships between the things are not just table relationships, but actually algebraic relationships. If you multiply two planes, then you get a rotator. We have seen several examples of that, and I'll demonstrate it as well. So this looks like a very nice system. What you don't see in here yet in this picture is where are the forces, where are the momenta, etc. So we're going to have to extend this a little bit from this simple object picture to a dynamics picture. So we'll probably have to make another mug when we're done. The main focus of this talk will be on this part, because this is where the motions are. Not the reflections, because that's not Newtonian mechanics, but just the continuous motions. So just to rehash a little bit, if we have two planes, we also have an operator that makes the intersection between the two planes. That was the wedge, and that produces a line now on the coordinate basis of, well, the composition of two vectors, so all the possibilities that you can make in the PGA to do that. If you do three planes, and maybe this is a good example to do in a little bit more detail. So how do I make a point at a certain location from the origin? Well, I take a plane maybe, perpendicular to the x-axis at a certain distance, perpendicular to the y-axis, perpendicular to the z-axis. I do the wedge, so that meets all these things. And if I do this, here you see this first plane in E1 direction with x1, E2 direction with x2. You just use the wedge product to compute this, and things naturally group into something that you can then briefly write as E1, E2, E3, that's the point at the origin, that's where the three origin planes cut, plus x times something at infinity. Okay? Doesn't matter. There is apparently something with a coordinate 1 and something with the coordinate x1, x2, x3 that I need, and that is precisely what we would recognize as homogeneous coordinates, except that the basis on which this is now expressed is the 1 goes with the E1, 2, 3, and if you see where the x1 goes and you look that up in this equation, you see it's 0, 3, 2, 1, etc. These are actually the points at the coordinate directions at infinity, and by making a combination of these things, I can get a representation of a point. So you see that these pictures we've seen from Stephen and from Martin of the three intersecting planes forming a point because it's a point reflector, etc. This is the computation that goes with it. It's extremely simple. It's just using the properties of the wedge product. There's something very unusual going on in this representation. It's actually also true for homogeneous coordinates, but I'd never really realized it. So let's say that I've been at the origin and I move over a distance p to a point that I'm interested in. So I would represent this as the object O plus pi. We've just derived that. Now, this is one algebraic object. It's a trivector. I can add something to here, which I then have to subtract something from here so I don't change that object. And now it suddenly takes this form. R plus p prime, it's p minus r, here it is, times I. So it's almost as if my origin is now this, and the point that I am looking at relative to the origin is that. But of course I could have done that for any point. So there's a very strange freedom in this thing. It's very specific about where the point is. I have given it coordinates relative to the point that I originally constructed it. But once I've made this object P, it doesn't care anymore where I want. If I want to stand here, it remains itself. And if I then inquire, yeah, but what are your coordinates? Then I have a look at the vector of I, and then it says, well, the vector of I is this, because you're now standing at R. This is totally automatic. You never have to worry about this. You make the object once. It doesn't care in which coordinate system you made it. No, translationally invariant. That's really very handy. If we want to describe things in their absolute relationship relative, not relative to a place where I used to stand and just defined it for the first time, then this is exactly what we want. So there's a very strange paradox here that you can give it coordinates and you make something that is coordinate free, which you can use from anywhere. You can always ask the question, okay, now that I stand here, where would I see it? But you don't have to change the object for that. So if you set up your equation in terms of these things, they will be totally coordinate-free equations. We have another way of making lines. So there was one way of saying I make it the meet of two planes. If I do that, then I usually have plane 1 and plane 2, and I would say that there's an angle between them. So this is clearly sort of like an axis, something that I can rotate around. When I have a point that starts moving, I am more interested in it was here, it goes there, and I move in this direction. What is the line of movement? This has been called a spear. It doesn't have that rotational aspect of it, it has the along aspect. So one of them is around and the other one is along. Both are sensible ways of talking about lines, but if you just look at the coordinates, you cannot distinguish them. They look like the same sort of thing. For us, it's going to be important to make a distinction between them, to make a dimensionally independent, ignorant, agnostic way of characterizing dynamics. So, axis is something we turn around, a spear is something we move along. And these will be the things that will model momenta and forces, but then we're 20 minutes further down. Representing Euclidean motions, it's the only picture I could find of a screw around the time that screw theory was invented, so I thought I'd steal it. It's now going by itself, which is not what I wanted. That probably killed it. The basic organizing principle, we've seen it several times, is Cartan-Dieudonné. You know, we see motions as multiple reflections. We're not going to do them as multiple reflections, but we're going to represent them as if they were. And one of the central things there is the sandwiching, which is that if you want to reflect an element x in a plane A, then you have to do something like A times x times A, except that if A is not normalized, you better normalize this whole thing so the norm of A doesn't occur. That means you should better use A inverse. And if you look at properly what you want, if a mirror reflects in itself, then maybe you want that if this was the reflecting side, then the reflected mirror should have the reflective side here. So let's maintain these signs properly by putting a minus sign in it. But as soon as we start doing two of these mirrors, so I have one here, and I reflect the result of that in the other one, you see that the minus signs disappear anyway. As long as we're talking about these even motions, these motions that I can perform continuously, the rotations and the translations, and forget about the reflections, this doesn't really matter anymore. So this is the way that we perform the mirroring algebraically that Stephen drew in his pictures, and Martin as well. And why does this work? Nobody showed this, and I think it may give you a little bit of a handle on the connection to linear algebra. So in linear algebra, you would say if I want to reflect x in something with a normal vector A, then I would have to take twice the projection and subtract that from my vector. Now in geometric algebra, we say, yeah, but the dot product is just the symmetric part of a geometric product. So I take xa plus ax divided by 2, and then I have the symmetric part. And if I now allow myself, multiplying these things out, have an obvious thing that a squared divided by the norm of a squared, that should be 1. Okay, so that means that a squared should multiply to a scalar. Then I get to this equation. So there's a correspondence between the old way of doing it and the new way of doing it if I introduce a new product, and this, wanting this to be true, dictates the properties of that product. So now we get sandwiching. Like I said, there are some minus signs, but we're not going to bother about those because we only do even transformations. And the nice thing about the sandwiching now is that it's equivariant. So whatever you put in the sandwich behaves correctly. What do we mean? If I had made a line as the join of 2 points, then I could have moved point 1 point 2 and made a new join, or geometric algebra allows you to actually transport the whole line. The result is always the same. And why is it the same? Well, because you can always put these m's in there. So for a geometric product, it's at least so that this property holds. And now as long as we make objects only as linear combinations of geometric products, we will always satisfy that for everything. And that's what we're going to do, because the weights product, the dot products, and all these other ones are like that. So this means that you no longer need a method for every data structure. You don't need to specify how a line transforms. Martin was talking about that. The lines, the points, and the as matrices acting on the vectors that represent lines, points, and planes are all slightly different. In geometric algebra, it's all the same, and a motor does it. And these equations haven't been really shown, but I just wanted to show that indeed the wedge product is a linear combination of geometric products. It's the anti-symmetric part, and the other one is the symmetric part. Now, we've seen many pictures of making two planes to make a translation, and we've seen something about a gauge transformation. Let's just do it. So let's take two planes with a normal vector n, but one at the location d1 from the origin and the other from the location d2 from the origin. Is the origin necessary? No, by the same argument I just showed. These are just objects that are independent of that origin, surprisingly. If I just do the multiplication, then n times n, I've normalized the normal vector, is 1. And here I get some others, and E0 times E0 is 0, so that doesn't appear. And now we see just the gauge appearing. Right? The only thing that is necessary to specify this translation operation, even though I started with two specific planes, is that the only thing occurs is the distance between the planes and the direction that the planes had. So I can characterize this by a translation vector, and it doesn't matter anymore which planes they are. We saw animated constructions of why that would be when you divide 2 points to each other. That might have suggested that you have to do something for it to make this true, but it isn't. It automatically happens. It automatically is so that these pieces are put together, and therefore delta 2 minus delta 1 is the only thing that matters, so it doesn't matter if both of them get 100 times further away. It just cancels. And the same thing we see with the rotations. If I take two general planes and I do the product of one plane with the other plane, so I reflect in one and then I reflect in the other. If I put this in the sandwiching product, then there's a bit of hocus pocus in which I should recognize that I'm actually talking about the common line at a certain location, but it is indeed that line. The hocus pocus you can figure out in one of the tutorials. Again, you see that the only thing that apparently happens is the line between the angle between the lines is relevant. And the angle between the planes is relevant, and the line that they have in common. And so again, all these specific things like I used N1 and N2, but you use these two, doesn't matter as long as they have the same angle and the same line in common. So again, this completely cancels out automatically, and you can call it a gauge transformation, but yeah, it's just as easy as subtracting two things and knowing that therefore their absolute values doesn't matter. We will write these things in the exponential form. Joan mentioned that briefly. I understand that you have had Taylor series and exponentials. If you write this out and you just remember that every time you get L squared, you can replace it by -1, then you will find that there's a lot of things that only are scalars, and they become 1 minus phi over 2, phi squared over 2, plus 5 to the 4th over 4, over 6, 4 factorial. And those group into the cosine, and the rest groups into the sine. So this is equivalent to that. And yes, looks a bit like complex numbers, looks a bit like quaternions. If they're in the origin, if this line runs through the origin, this is a unit quaternion. And otherwise, it is a special case of a unit dual quaternion. Now, so this is nice, because what we, for instance, could say that if we want to generate a motion that rotates around an axis, then apparently all I need is the axis itself and the angle that I want to rotate over. and I make this operator, use it in sandwiching, and I can turn anything, because we've also seen that it works on any kind of an object. So there's a direct correspondence between specifying motions by their geometry. Maybe we want to revert that as well. So maybe we want to take a motion and then identify its axis. That's what Martin discussed. That's the exponential versus logarithm and finding how it actually moves. A little bit of a strange thing that we have to get used to is that, and I've drawn it in gray here, that an axis is something you turn around. So you use it finitely to make a rotation like this. If your axis is a line at infinity, and you turn around that, then if that would turn like that, I would feel myself moving up, right? So this is how I describe a translation. It's also an axis, but it's an axis at infinity. As long as we agree that that is allowed in our terminology, the algebra suggests that. But then when we want to make a general Euclidean motion, it becomes a bit subtle, and Martin has shown that. You are not just allowed to add the parts of the two components. One of the things you can do that shows that it's ugly, that if you take a rotation first and then a translation, which is the common way you characterize motions in homogeneous coordinates, you get something that looks rather draconic. There is a grade 0 part, a grade 2 part, and a grade 4 part. Yes, but you can still write that in the form of the exponential of a bivector. If you want to know which bivector, use the algorithm that Martin presented. But this can still be written in the form of this. And if you then want to understand what this bivector looks like, you can still look at Martin's stuff, and you find that you can always write that as a combination of two things. There is an axis that is being turned around, and at the same time there is an infinite axis that is perpendicular to that, which gives the translation. So you get this screw motion. Is this a good representation of motions to do interpolation and so on? Well, that depends a little bit on your application, but it's certainly an algebraically unique way of describing what this motor M looks like, so that I can characterize it with 6 numbers, the 6 coordinates of the bivector. If you want to compute with that, you maybe think that you have to do very complicated things, but Martin and Steven in their paper, Normalization, Square Roots, Exponential and Logarithmic Maps, give extremely compact code to take the logarithm of a rotor and to take the exponential of a bivector with very, very few multiplications. So this can be implemented really quickly. I've said that one of the advantages of the PGA is that there is an interrelationship between the motions and the objects, which other motion frameworks do not have. You go to a completely different space to represent your motions, or so it seems. But the ratio of 2 planes is a rotation. The ratio of 2 points is a translation. The ratio of 2 lines is the screw that turns this line and moves it at the same time, perpendicular between the two. And these are simple constructions, that's why the square root comes in, that tie the objects that you want to use to define motions to the actual motion operators, which then are capable of not only moving those objects, but any object, because sandwiching is equivariant. Yeah, so that's a really very nice consistent framework. Maybe we should try to use that for physical motions as well as motions in graphics and robotics where homogeneous coordinates are used. Now there are different ways of talking about motions now. We have homogeneous coordinate matrices. We can use quaternions for rotations and then translation vectors. We can use unidual quaternions, which are more like the motors, or maybe we want to characterize them as these screw bivectors, which are only 6 components, whereas the motors are 8. Steven and I are supervising a UVA student who is going to use these different representations to learn motions from observations, and we are currently finding out which of these representations are most suitable for neural networks to actually learn the motions. And there's some subtleties here. If you just use the screw axis representation, which seems algebraically very nice, uniquely defined, even physicists agree among each other which bivector decomposition works, then it still makes a difference whether you do that in a global coordinate system, which is the yellow axis. So the yellow axes are for each of these little motion steps that I do here. And at one moment I rotate around this axis, now and the next moment around this, because I'm sort of working with a translation, versus the local coordinate system where I travel along and say only the relative motion is this with this axis, and that is indicated in blue. So even when you choose for the bivector representation of motions as the log of motors, there is a choice to be made of how you apply that. And this looks much more easily learnable than something like this. A network would really have difficulty with these things that go to infinity. But we're going to find out when she's done in a month or so. A little bit further, because we're actually now talking about motions, and we will of course want to talk about differential motions, because we know that Newton's equations are differential equations. They say the next time step, this is going to happen because of that. If you look at a motion that is encoded like this, so I have an object x0 that is being moved by a motor, then if I want to characterize the bivector of that motor, I can actually derive that from the motor as saying, well, it is the derivative of the motor divided by the motor itself. So it's the relative motion, the relative motor. That turns out to be always a bivector, and that is indeed precisely the instantaneous bivector that you need. If you then say, yeah, so this now means that I have at this moment I have a small axis that I'm turning and twisting around, what now happens to an object X? Then it turns out, and there was also a picture that was on the slide, one of Martin's slides, that such an X moving under the influence of a motor M will get a little derivative that is actually the commutator product of X with this bivector. So the bivector gives complete information about the local instantaneous motion of any kind of a thing. This is not just for a point, this is also for a line, in CGA for spheres. That is how simple it is to take a time derivative of something that is moving under a motor, but you have to know the bivector. And note that there's nothing here that says what kind of a motion it is. This bivector contains both the rotating and the translating motion, so both the linear and the angular velocity rates are in here. I will call this the rate bivector if I do it as a velocity, as a time, certain constant thing per time step. Now, you can either accept this or derive it. The actual general derivation is a bit tricky, because you have to somehow prove that this is always a bivector. But let's look at a very specific case. So let's give a motion with a constant bivector rate. Even there I have to be a little bit careful, because I have my object x0 in my coordinate system, in my graphic system, or where I have defined it. But it starts moving at this location and then starts evolving. So what I just always have is that there's an initial situation that I put it in. This is a rotation translation, therefore it's a motor. And then I start evolving it. So if I say I want to evolve with a constant bivector, it'll look something like this. First do M0 in the sandwich, and then multiply by this. Now, the time derivation of something of this form is very easy. You know that an exponential function just is the derivative of its argument times the original function. So this takes this simple form. It was true in calculus, it's still true in geometric calculus. So this is indeed, here we see m dot, here we see bw, the bivector in the world frame, and the motor itself, and that gives that equation that I had on the previous page. Sometimes it might be more handy to say, well, let me first, this thing is evolving, and then I put it at the place, I take it in the origin, I start evolving it in the way I want, and then I put it in where my origin actually was. And this is called the object frame motor. So now I first do my evolution, like a spinning top. This is a very natural thing to do. And then I say, oh yeah, and by the way, the top was over there in this place. If you now do the time derivative, you see that the B is in the other side. So there's a slight difference between world frames and body frames. And when we do the evolution of the Newton equation, it'll turn out to be slightly handier to do that in this frame. But it's an easy switch between the two. How does this commutator now come about? Yeah, well, if I take the time derivative of something that is so composite, I have to take it of the first term, and then I have to leave these alone. This is constant, and then I have to take the time derivative of the inverse. Well, I looked it up in the table. Well, in my book, so I first wrote the book, and then I have to look at the table. I wrote the book so that I could look at the table, but this is in all the books, Chris and Anthony's as well, David Hessenes. This is how the inverse differentiates in time. And then you regroup the things a little bit, and then you see that this m dot m inverse appears here and there on both sides. You're not allowed to move it through there because things don't commute. We recognize that as either this one or this one, and we put them together. We define a new product that says half of AB minus BA is the commutator, and this is now shown for this constant rate that we indeed have this form. Yeah, but you don't need all those details. It does show that the computations are greatly complicated. Yeah, okay, so you have to know the derivative of an inverse, but it's not that hard. Let me keep an eye on the time. Let's say? Plenty minutes. This animation doesn't work now. So we're going to represent a motion by a momentary axis. We're going to expand movement, so a thing that is moving by a local join line. And the correspondence between the two is going to be the inertial mass distribution. And then I wanted to pop up that maybe this doesn't mean much to you, and it just looks saying thing 1 and thing 2 without giving too much details. That's what we're going to do. Cut, Benny, for the video. And so now we're going to actually Newtonian motion. And I have the feeling that it's automatically walking ahead now. Maybe not. So to go, what we just done is the relationship between if I rotate something, how much does something move? And that you can call that kinematics. And the description between a little change in the parameters of the motion and how much it makes things move. We've done the following steps. We are said planes are reflectors in sandwiching. Even reflectors generate a motor. And we're going to represent that by a bivector, which is like an axis. The bivectors of R301 are compact parameterization of the 3D Euclidean motions, precisely the 6 parameters that we expect to have to say, because there are 3 angles involved and 3 translation things are also number of parameters that are in the bivector. They weren't in the motor. A dual quaternion motor has 8 potentially independent parameters. So also for a neural network, that may not be so good. And to convert that twist bivector rate to actual movement, we use kinematics. What we're going to do now in the second part of the talk is that every movement has a momentum, and that'll be an element from the PGA that is called a dual bivector. We were going to unify forces and torques in something that Stephen calls a fork, because he's funny. And Newton-Euler says that a fork changes momentum, and that gives you the differential equation, which you can then integrate numerically. Okay, so here's a big thing in the middle here that we have to work towards. So let's say we have a heavy point. So we have a point with mass m at PGA trivector location x. Let's move that a little bit. What happens? It gets momentum. What happens is that a little bit later, it is at xi plus xi dot. But we know what xi dot is. You know, that's xi cross b, if we know that it's moving under a motor with bivector b. And that's the only thing that happens in the joint. So I'm going to stand with the heavy point at this point. I look at a little bit further, and that little bit further is determined by that bivector, because it is doing a momentary motion according to some kind of an axis, which I still have to determine, but that is the relationship between the two. Now, when you look at this expression, this tells you something about, if I do this for all the masses that are in this composite object that I am moving, oh, that's not a rigid body, okay. This composite object that I'm moving, then I have to add all these contributions, and you see something with the x occurs twice there, there's the mass. Depending on how the masses are distributed in space, this will be a different number, but it will be very characteristic for the set of things that I am moving. That's called the inertia. And in this expression, we just say this is a linear function of b, let's call that linear function I. It depends on the particular mass cluster that I'm trying to move, but I can compute it beforehand. And every time I can say, okay, now this mass cluster has to rotate around this axis and shift a bit. What happens, how hard is that? You compute this momentum to say how much effort, the amount of movement that involves. Seems completely innocent, but you may not trust that this is the same inertia that you may know from classical physics. It is if you do a very stupid split of the bivector into, let's say it rotates around the origin and there is a translational component, and you do the computation of this function, then you will find that there will be a linear momentum involved with, relative to the centroid of this object, that is something like the v of the centroid plus a little bit that it's also rotating because of the b, plus something that you recognize as very close to the classical formula for how you compute inertia and angular momentum. So I want to open it up only later at the end of the talk, but it is in there. This looks completely innocent, but the B contains both the rotational and the translational aspects, and this mass inertia, total inertia that we compute, also still is completely capable of processing how hard it is to translate something and how hard it is to rotate something. It's all in there still. It's just surprisingly simple. So we have that one. What happens algebraically? Well, we put something in that was an axis, and it gives something that is one of those join lines. In 3D, that's very confusing because an axis is a line and a join line is also a line. One of them is a round line and the other one is in a long line. But if you would see this in 2D, your hyperplanes are lines. So an axis is the meet of two lines. So in 2D, an axis is a point. But when things start moving, when points start moving, they move along lines. So then in 2D, you see a clear distinction that one of them is a 2D bivector, which is a point, and the other one is a 2D vector. You know, 2D has a 3D PGA, and 3 minus 2 is 1. So there is a duality relationship between the two. And that is indeed true. This is a duality transformation, and you can easily implement that. And when we look at Stephen's code, that's also what he has done. So it is always so that there's a relationship by the mass distribution between the axis and the motion. Inertia in PGA is additive. Classically, you don't have that. I don't know whether you've done classical computations with inertia matrices, but you have an inertia matrix of this object in this position. You have another inertia matrix of this in this position. You now say, I want these movements to be one object that moves together. Then I have to do an extra computation that says how you have to convert this inertia matrix from the coordinate system of this, or maybe from the coordinate system of the common centroid, to get the total inertia of how hard it is to rotate this total thing. So there is an extra thing where you have to think of what to do, and you shouldn't forget it, because then you get the wrong answer. With this inertia, it is completely additive. So how this composite object reacts to a bivector rate is just the sum of how each of the individual ones do. And that is again related to that same property that I showed you for a point, that you can define things that don't change no matter where you think your viewpoint is going to be. The object remains the same. If you ask the question, you can retrieve what it would be in those coordinates, but just don't ask the question. Don't ask policy. The time derivative of something like an inertia, well, it's a linear map. It moves with the motor, so we will at least expect something. If anything moves with the motor, you get a cross B. But in general, also the B itself may vary. This is a linear function, so the ddt just goes through there. So this is the total derivative of what we expect for the inertia map. And now we're almost there. Oh, we should talk about forces first. So let's say that we have a force. What do you have to say? Well, the force moves along a line. The force acts along a line. So let's take a point on that line, the point Q, and let's take the force vector in Newton, and let's make this join line F dot Q. I was maybe a bit fast in the slide where I derived the join line, but if you have a point Q and you want a line in the F direction, then the geometric algebra object that does this is F dot Q. And this is a dual bivector in our case, because this is a trivector, and a dot product lowers the grade by 1. So it's a bivector, but it's a dual bivector. This has exactly the same sort of properties as I showed for the point. So if we define a force along this line, this blue force, this just exists in space, and it is just represented by an algebraic object. But if I want to move point R and say, what does this object, this force object look like from my perspective, then okay, let's first write it like this. This was O plus Qi. Let's now introduce the Ri, because apparently we're interested in something in location R. Then we have to subtract it here. This organizes completely into something that I recognize the force at R, just like this was the force at Q. But apparently I get an extra term, and I have to do some manipulation to bring it in classical form. But this turns out to be just the torque that I feel at that location. So again, this one fork object remains the same. If you want to know what it is from here, you sometimes may feel a torque. If you displace yourself along the line, you will still only feel the force. Look. But it is all exactly the same object. You don't have to peel it apart to find out what it is. It just is. So that's very handy, because now we can set up the general equation of what is going to happen. A fork, combination of forces and torque, causes a change of momentum. The momentum contains the linear and the angular momentum. This is the equation we need. The P was that thing that we had, which was the I of B. We maybe want to do it in the body coordinates, so that means that the world force is this thing, which was the derivative of that of P in the body frame, and I now have to place it at where I want to be with the forces. You know, I'm doing my computations here, but that means I have to translate, for instance, the gravity force may in my coordinate be rather skew, so I have to transform that back. This is all done to make it slightly easier. We now have to unpeel, because we're interested in the B dot. We want to see how much we have to change the present B that we think it is. And that's just an inversion of this function. And then once we have what B then is, in the next time step, we still have to make the new motor out of that. So there's a coupled set of two differential equations. One says the force via the inertia causes this change in the axis you're turning around. And the other one is, oh, if your axis that you're turning around is this, then your new motor will be that. And this is how it integrates. Let's see a demo. Oh, this is not the one I wanted to show. This is, for instance, one of those things that we can demonstrate. So here we have a block that is hanging from a certain thing with a string. I can run it again. And if you look at the equations, then you see that I have defined a force of gravity. There is a hook force, so that is the attachment point in one location. Here you see how that is done. Or I had a slide for that. Let me go to the slide. At least you see it works. Let me go to the slide first. So here's the code in a little bit more detail. So we have a point in real space that I want to attach one of the corners of this cube to. Here you see what happens. This is the corner of that cube. It's a point with index some number. In order to make the relative line between those two in which I have to apply the hook force, I should take that attachment point in the real world and use my inverse motor to apply to this, so I transform it from the world system to my local coordinate system. Here you see the momentaneous bivector we use to make some damping, otherwise the thing goes numerically a bit unstable. And the gravity force is done by one of Stephen's handy operations. This is dualization. So we first define the infinite line. The E2 direction is vertical. So I have a plane that lies like this, perpendicular to the floor plane. It meets infinity over there, and then to get an arbitrary vertical line, I just take the dual of that. So that's how he has constructed this. And that just works. And what do we have here? Here we have set up the equations. If you remember that m dot was -1/2 m times b in the body coordinates, and the b is something that was the relationship between b minus the dual, times the dual, that is the inertia that is in here, because this is inertia that we have defined. In this example, that's the Hodge dual. This has some very nice properties. Steven has been talking about that you would really like to specify these things in a way that that doesn't demand too much on dimensions, and that you can do that because if you characterize things by their normal vector, then you say my normal is in the direction E1, and I don't care how many other dimensions there are. If you want to know what others is on this plane, then you have to evaluate any point with an arbitrary E2 coordinates, E3 coordinates is also on there, or maybe E4, or maybe E42. The only thing I want to say is it is perpendicular to the E1 direction. So here he has implemented that. There's a nice video of him programming this whole code in real time. It takes 10 minutes, but you gradually see it develop. And the interesting thing now is that I have said here that the dimensionality is 2, and that's the initial thing in which he programs it. Then he makes the dimensionality 3, and automatically it changes the block. You have to look very carefully to see where the dimensionality affects the thing. Well, the number of points to make a cube in that dimensionality is relevant, and he attaches it to the last attachment point. I've always been in favor of calling this the 0th point. Then you will see that in all of this code, also in the specification of the forces and in the equation, the dimension d does not occur. So this is totally dimension independent code, and in order to drive that point home, we can even make it a 4-dimensional thing, and now we get in 4 dimensions we get a sort of poor man's 3-dimensional. You can't drag it in 4 dimensions, okay. No drag queens in 4 dimensions. But this is just the same kind of thing. The code is exactly the same because it has been specified not only in a location-independent way, coordinate-free way, but it's even been specified in a dimension-independent way. And there's no other system that can do that. Okay, we'll go to the summary then. So The path we have walked is that we have said that if we start with hyperplanes and we meet them, we get a line which is like an axis. And if we put a rate around this axis, then we get a motion operator. Then we came in with a force. And we have seen that a force is a different type of line. It's an along line, it's a join line. And you could make those by the join of points, just like you made these as the intersection of planes. Now, there was some kind of a relationship between the rate of change and the momentum that that caused, and that involves the mass distribution, which is encoded in the inertia. And somehow we have to work our way back up to the b dot and the m to get out of this, which also involves the inverse inertia. But this is the relationships between these things. So the algebraic elements of the dual line and the line, the meet line, are the two important things. This is a bivector, this is a dual bivector. This encodes this encodes that, and the whole is related in this manner. Now, that's too nice, so let's break it, right? So we're going back to vector mechanics, because all these coordinate-free things, and we don't understand them. We really only like vectors. So let's forget that we know about homogeneous coordinates. That's something for graphics people, for roboticists, not for true physicists, because we all know that space is three-dimensional, so why would you use something four-dimensional to represent space, right? Okay, you want heavy points, and so you have three coordinates plus you have the mass, but let's ignore that. Let's say mass is something completely different, doesn't belong in the geometry. Okay, so we forget that. So that means that we lose our vector E0, and that means we now have to trade. We don't have that there are rotors that make something rotate, and exactly the same kind of rotor that make it rotate around an axis at infinity, which is translation. So we have to treat linear and angular separately. Then we automatically have caused that, but we like it that way. Now, we're not using bivectors because we don't understand them. We just use vectors, but we notice that some of the vectors react differently than other vectors when I do reflections or motions. So I have to now introduce two kinds of vectors, polar and axial vectors. One of them are for linear momenta, and the other one are for angular momenta, which react differently. And yes, they're both three numbers, and I'll just have to tag it or have to mind my software so that this goes correctly. I know that my force acts in a certain line, but I want to characterize it with a vector, so I can only give you a force vector, and then in the text I say, oh, this was at point Q. No, I can't make f dot Q as an object because I don't have that. So I always have to go back to the text when I want to go to a different place to see where this was evaluated, and then I have to put it in there. So I need all sorts of extraneous techniques to get my inertia right when I go to a different place, because it's not part of my math, because I haven't encoded it in a vector. And then we tell our students that is how nature is, so you have to get used to it. And we do that for a number of years. Actually, they could have changed after screw theory, which has some of the aspects of the things I was just talking about. If you do that, then this framework, which was, as I showed you in the software, was all we needed. We needed to specify some details of the forces. We needed to specify some details of where the masses were. But then this was a completely automatic framework with two lines of integration. That then becomes something in which, indeed, the linear and the angular aspects are completely distributed, in which if I move to a new location, I have to remember that my inertia matrix is now no longer that, but I have to add all sorts of things because I've moved to a different place. And the same with what happened to the angular momentum when the offset of the centroid. I have to remember all these things, I have to teach all these things, I have to make separate sets of equations that integrate the linear and the angular, even though they are combined. And what I could have done is make a very simple construction. Whenever I have, let's say, a force, I say at which point I have defined that force works. And whenever I have a torque, I say, well, but that's really sort of, it works only on the directional aspects of the thing, so I slap an infinity on it. All of these things are just f dot r and e naught wedge, the other vector, the angular vector. These are the polar vectors. And this is just a dual of that, you know, for the rates, because it's just opposite, which is also a bit confusing, right? So now the translation is here, and here the linear motion is here. So there's something strange going on even classically. All right, because now, and what I could have done is lifted it by taking my classical vectors, and I could have done the linear aspects dot the location where it acts, plus E infinity wedge my angular polar vector. I could have made one PGA dual bivector that is completely equivalent and decomposable into this, but that has much nicer algebraic rules for integration. And that lends us back to this thing. Because I have -2 minutes left, I will. So this is all not totally new, in the sense that in other frameworks it was also recognized that there is a 6D structure that is rather linear, that you can appeal to encode the dynamics. We have PGA, but there's also something that is much older, screw theory, and there is something that is used quite a bit in robotics and in Muyoko for coupled motions of things under constraints, that has been developed in something called spatial vectors. These are 6-dimensional vectors. Any of the 6D frameworks is already a bigger improvement over the two polar plus axial 3D frameworks, because it starts integrating these things. There is some hairy math involved, which for us is completely automatically taken care of by the bivector math of PGA. We have this naught, E0 in there that automatically cancels some terms that you don't want to appear if you would do a normal product. The other frameworks have to hard code in special multiplication rules that are different for whether you're a force or whether you're an angular rate. And that is how spatial vectors do it. The advantage of doing it that way is that you get completely into standard matrix and vector operations, and so you can use existing linear algebra packages and optimization in there to do that. But they're also disjoint from the objects. It's a special motion representation that you jump to do something, and then you come out of that and you move your objects. And we've seen that for us, that's also more integrated. So PGA really cleans things up. Objects and motions in a nicely integrated framework. Bivectors are the crucial motion representation. We unify linear and angular. The inertia is additive, which is addictive. They're very simple and efficient code results. You've seen some of that. And it's easy to upgrade to it, so why wouldn't you? More information about these things, we've written some tutorials, and the software is on bivector.net, because all the cool vectors are bi. And here's some more exploration. All right. Any questions? Which slide?
You didn't mention the 5D approach, which Chris and I and Robert did back in 2010 for the Amsterdam proceedings. So I believe that does the same integration here that you're talking about in terms of joining together the angular and linear side. What I'm not clear about is whether it satisfies this origin-free aspect. I don't know if you have any thoughts on that.
I should look at that. Amsterdam, you said? I've heard of that. Oh, you mean the 5D as in embedding it in CGA?
Exactly.
Oh, okay, yeah, okay. Now I thought you were talking about the 5D for this as opposed to the 6D bivector. Yeah, so what you find is that back in the days before we had PGA, we did Euclidean motions with CGA because, well, one, because we didn't have it, and the other one, when it did come about, we thought that the duality was much more easily done in CGA. And so PGA sits naturally in CGA, but you don't need it to do the Euclidean motions because you can do them as multiple reflections in planes and so on. What Hugo has done with Joan was that when you want to extend this thing, there are techniques. For robotics, it's a lot more interesting that there are constraint motions, but all these things are connected by joints, and these joints are often spherical. You want to move along spherical constraint, perhaps. And then it turns out that I get my inspiration from the spatial vector book, in which they process these constraints as linear conditions and then propagate them through their system. When you use CGA, and you have a spherical constraint, then that also becomes a linear condition that you can automatically then integrate into the system in the same way. So for the basic motions in free space, there is no need. This works, but it is true that when you move up to CGA, you get basic objects that you can use to impose your constraints, among which there are very sensible objects that very often occur in robotics type applications, like a spherical joint that you want to move around. And that is what Hugo has worked out in, what was it, 2-3 years ago, in a paper there. Yeah.
Constraint dynamics in, something like,
Yeah, so I had one demo also made by Steven, of course, where we included some of these constraints. So here, for instance, you see an object that clearly is not moving freely anymore. It actually feels these things. What we did, I just went to the wiki page of constraint management, and it was a very direct translation of that algorithm into the geometric algebra way of processing the fact that you can't move further than you wanted to in this particular direction. And that also, delete, run. That also then works, automatically in 2 and 3 dimensions. It doesn't matter in how many dimensions you set that up. Here you see the local velocities dragged along the thing. This is actually something that is on an inclined plane with some gravity acting and contact constraints that that give you an impulse at the moment that you collide with it. What I see is what I've done in Moyoko is the basis of that is all the Featherstone stuff in the spatial vectors, but the translation from that way of looking at it to embedding it as constraints into PGA for the linear constraints in planes is obvious. If they would be spherical constraints, you'd much better off using the CGA extension to PGA to also embed those. And if you have, I don't know, ellipsoidal constraints, maybe you use another type of algebra. But you can, again, that onion structure of GA, of the nesting of the different algebras can be applied here as well. But it's more useful for the constraint management than for these free motions.
Yes, GA is just like an onion. Makes you cry.
Yeah.
All right, we have a 5-minute toilet break, I think, and then we have the apotheosis of the game conference.
Oh, I forgot to make one joke about this table, that the decomposition into classical, it's called decomposition because it stinks.
Also the moment of appreciation, Leo, you don't need a fork for this. And my students will kidnap you.
Right. I apologize to the next speaker. Is anybody keeping an eye on the SpaceX launch? Is it going? It's the first launch window is in 20 minutes, so we'll either watch that or Anthony, right? We might, but yeah. It's likely to be a countdown that is stopped at a certain point, and then you don't know when it continues. And they have a launch window of an hour. I don't know why, but it's probably the clearing of the airspace or something. How does that mouse get in? This is mine. Yeah. Do you want one? No, I'll bring one. Yeah. Mine is.
Testing, testing.
All right. Benny, are we... Okay. I'm just going to check the stream. Yes, perfect. Okay, so it is an absolute honor to present Professor Anthony Lazenby, who is Professor Emeritus of Cosmology and Astrophysics at Cambridge University, and he is probably the #1 researcher working in geometric algebra today. His talk is going to get you through all of the fundamental forces of nature, and the subtitle, A Geometric Tour de Force, applies both to the content as well as the person that is delivering it. So I'm very, very proud to present Anthony. Thank you.
Thank you very much, Stephen, and thanks for the invitation to come here. So I'm going to be talking about the fundamental forces of nature. And the idea overall is to explore geometric algebra as a language in which to do physics. And the conclusion is that it's extremely useful for physics and enables us to reach quickly advanced areas that other mathematical languages, such as vector analysis, complex analysis, quaternions, matrices, spinors, tensor calculus, a big list. They can only each individually cover whatever area we want to look at partially. And it takes often a lot of time and dedication to get into. You really have to devote, sizable fraction of your life to understanding things like tensor calculus properly. But what I want to do today is take you through to some advanced areas, equipped basically with just the geometric algebra of 4D space, which we call the space-time algebra, or STA. And the advanced areas I want to get through to, they'll all be associated with the fundamental forces of nature. So it's an ambitious program, but because of GA and STA, we're going to be able to get to these really quite advanced areas in this single talk. So here's a bit about the 4 fundamental forces of nature. We'll be looking at each. So there's electromagnetism. That's down here on this table at the bottom. That's the easiest one to start with. That's got a range of infinity because the particle which is meant to mediate it, the photon, is massless. The other force which has a hypothetical, it must be said, mediating particle which is massless and therefore has infinite range is gravity. That's extremely weak. And then you have something called the weak force. This governs particle decay and is short range because the particle carriers you see here, the W and Z particles, they are massive, really quite massive. And then finally, there's a strong force that binds quarks together, and the thing that binds them are the gluons, and we're going to be looking at those later on. And this is very short range, again, because what's involved is massive. So those are the things we want to look at. Now, how do they work? What's the general sort of principle for these? They work via invariance under groups of symmetries. So we're going to explore these symmetries using the tools of geometric algebra and the STA. And as part of this, I want to explore something that until recently I had thought stood outside the main line of GA development. Now, we know in detail from what's happened so far at this meeting that GA is very good for understanding both complex numbers and quaternions. And you can view complex numbers as the even elements of the GA of 2-dimensional space, and quaternions as the even elements of the GA of 3-dimensional space. This is what they turn out to be. However, you may know that both complex numbers and quaternions are what's called normed division algebras. We'll look at that in more detail, but basically what it comes down to is you can take any 2 elements, each of them has an individual norm, and when you multiply those elements together, you get something that has a new norm, but it's the product of the old ones. And they're division algebras because the only thing that has 0 norm is 0 itself. So you can always find a non-zero norm for everything else. So there's a third such algebra. It's called the octonions. And these haven't been terribly popular historically because they are a pretty strange object. So we know, well, that complex numbers are associative and commutative. So they function just like the real numbers in that sense. Quaternions are at least associative. So AB times C is the same as A times BC. But of course, they're non-commutative. And octonions, however, they're neither associative or commutative. And the lack of associativity looks like it's a really big barrier to using them in physics. But we'll see, in fact, perhaps surprisingly, that they can be represented nicely as even elements of the geometric algebra of 4-dimensional space, the space-time algebra, which are otherwise known as direct spinors. So actually, there's quite a neat thing here. We have complex numbers, quaternions, and now the octonions as the even subalgebra of 2, 3, and 4-dimensional space in the geometric algebra approach. So this is very interesting for us as regards fundamental forces, because octonions are recently used in particle physics to try to express the fundamental symmetry groups in the standard model. And a person called Cole Fury has been spearheading these recent efforts, building upon previous attempts over some decades. And these studies make use of something called chains of octonion multiplications, and these work a bit like a code. They're very clever because they build up things with quite high complexity from very simple building blocks, just like codes. And we're going to be able to start here on a similar analysis using just the STA itself to express these codes. And I just want to say something in the light of what Chris was saying yesterday. Chris was recommending we don't get hung up on merits of particular algebras, but treat them democratically based on uses for particular purposes. Well, what I want to do here, the emphasis here, is on the STA within physics. And I want to use it, or see if it can guide us as to the symmetries which nature uses for the fundamental laws. And the overwhelming good feature of the STA for me is that it's set in four-dimensional space-time. It comes directly from that. And that's basically something that we can be certain about. In the sense that we only know about 4 dimensions existing. And we know what the metric is. It's either 1, 3, or you can do it in 3, 1. So that is something that is actually there, and hence the geometric algebra of space-time seems a very good place to start on whether we can use the geometric algebra to tell us something about what the symmetries of nature might be. Right, so in case there are people who missed earlier lectures, I'll just give a brief introduction to the GA of 3 dimensions before going on to the STA. And more generally, there's fuller introductions and explanations of the topics here up until about halfway through the talk when we start on the octonions. That's all fresh material in this context. And but the previous talk I gave, which covers electromagnetism and gravity in more detail than we're doing here, it can be found on YouTube at this address. Okay, so this early material, we'll skim over it fairly lightly because you'll almost certainly know all of this. So in 3D, we've got 3 orthonormal basis vectors, E1, E2, E3, square to 1. They have 0 dot product, and they have a wedge product, which gives us a pseudoscalar for 3D space. And the dualization here is that I times any vector gives us a bivector. And there's a nice thing that I squared, this is doing this for complex numbers is probably the first way most people get the idea about what geometric algebra is. You take E1, E2 times E1, E2. Let's do it here with 3 things. And you can use here associativity plus swapping things according to the fact that the dot products are 0 to show that's -1. So you've got a real geometric object that squares to -1, and indeed you find there are many such objects as one carries on, which squares to -1. That means that we seldom have use for complex numbers as such. And it's a theme that will persist right to the end here of trying to see if we can do a good deal of modern physics with no complex numbers, but just the geometric algebra of space-time. So we'll call the highest grade object in the space the pseudoscalar. That's what this I is. And what can we do with this setup in 3D? Well, actually, what happens here is going to work in any dimension. Basically, the things we can do very simply, as you've been seeing a lot about, are reflections. Any vector A can be reflected in a vector n to give A dashes minus NaN. And it may be instructive to just actually work that out to see how it occurs that that's the case. The point is that minus NaN, when you expand it out using the rules of the geometric product, it comes down to this, A minus 2 n dot A times n, and that is indeed the way you reflect about a vector n. So reflections, they work straight away. Rotations, as you've heard many times here, 2 reflections form a rotation. If you reflect in unit vectors m and n, you get then m, n, a, n, m. And so the rotor is the bit here that we isolate off to give us something which can carry out a rotation via R-A, R-reverse. Reversion, it reverses the order of all products in between a set of vectors. And because of, let me just go back. And because of R being Mn, R times R reverse is then 1 when M and N are unit vectors. And this works in a space of any dimensional signature and for all grades of objects. So you have an object A of any grade, it goes to RA, R reverse. In 3D, you're used to this rotation being about an axis. What's really happening is, of course, you've just got a bivector here, and you're exponentiating the bivector. In 3D, you can refer that back to an axis via the bivector being I times n, where n is the direction. So that's really all we need to say about 3D, I think. We could just compare with the quaternions. So a quaternion is this thing here, A0 plus A1i plus A2j plus A3k, satisfies this. It actually turns out that they form what we would think of as a left-handed set. It turns out to get these multiplications working correctly, you need I equals IE1, j equals minus IE2, and k equals I3. So there's a minus sign in the middle there. But then you've got them perfectly. So let's go to space-time. We want to construct the geometric algebra as space-time. We know we've got this invariant interval from which we can read off the metric. And we're going to do that, we're going to need 4 vectors, which have the properties here. E0 squared is 1. And for I equals 1, 2, 3, EI squared is minus 1. So we're going with the 1, 3 version of the metric. And here's a summary of that. E mu dot E nu is the diagonal plus, minus, minus, minus for mu 0 to 3, mu and nu. So there's 6 bivectors in the algebra, and they come in 2 types. One of them is the wedge EI wedge E0, where EI is one of these things squares to minus 1. And then you've got those not containing E0, like EI wedge EJ. And for any pair of vectors A and B, you can see quite simply that if they if they have 0 dot product, which means that they anti-commute, you can work out that A wedge B all squared is equal to minus A squared and B squared. So these bivectors are going to have themselves squares that are either minus 1 or plus 1. And in particular, the space-like Euclidean bivectors, they square to minus 1. They're generating actual spatial rotations in a plane. And time-like vectors satisfy this, that they're square to plus 1. And they generate the hyperbolic geometry. And in particular, if we take e to the alpha E1 E0, that's the same as cosh alpha sine alpha E1 E0. And that is basically going to tell us Lorentz transformations very quickly. Now, we should just say something about the pseudoscalar of the space. We're going to use the same symbol I, and we'll be able to justify doing that in a moment. This is the same symbol as in 3D, but we define it here as E0, E1, E2, E3. It's grade 4, and it turns out that means it reverses to itself. And if you compute the square of it, it's another one of these things that gives you minus 1. And I provides a nice duality between bivectors. It provides a map between bivectors with positive and negative square, as you see here. So if you think of I, E1, E0, that's the same as I times something we're going to call sigma 1 in a moment. That's the same as minus E2, E3. And this, anyway, the sigma 1, which is this type E1, E0, that squares to plus 1, and the type here squares to minus 1. So that's why it gives a map of that kind. And you've got 4 vectors, and there are 4 trivectors as well. So we've got E1, E2, E3, which is a dual of E0. So there's 4 things you can take a dual of, and you get 4 trivectors. And I anti-commutes with vectors and trivectors in this case, and I always commutes with even grade objects. That would be a space of any size. Now, it's useful here to settle on a given fixed Cartesian frame of vectors to do your analysis. Think of this as the laboratory frame. I'm going to rename the E mu to be gamma mu because that is the symbol that would be used if you're doing this via direct matrices instead. And when you've done that, you've now got the basic tool. This is what we're going to use throughout for relativistic physics, the STA. So we've got the scalar. We've got 4 vectors we call the gamma mu. We've got 6 bivectors of these 2 different types, gamma mu, wedge gamma nu. Here's the 4 trivectors, and then a pseudoscalar I. And that's the space-time algebra, or STA. Now, gamma mu dot gamma nu is eta mu nu. Expand out this thing. This is the anti-commutator, the gamma nu, which is the same as the dot product. And that equals 2 eta mu nu. And that's the sign that we're dealing with the Dirac matrix algebra directly. That is the defining version of Dirac matrix algebra. But of course here, we're working with vectors, not a set of matrices in isospace. And it may seem obvious to us, having worked at it from this angle, that the gamma mu are vectors, and something satisfying this here makes sense from the point of view of the Clifford algebra and vectors. But it was about 20 or 30 years ago when I started first on this, it was incredibly controversial to point to this and say, these are vectors which are satisfying this, and not just the Dirac matrices. And people basically thought you were mad if you said such a thing. It was quite extraordinary. But anyway, we can see that it really does work, and hope to show you how useful it is. Now, we said think of this as a laboratory frame, or it's basically an inertial frame, and this can tell you how to form a set of relative vectors, and these are space-time areas swept out while moving along the velocity vector of the frame. So here's a gamma I, could be gamma 1, 2, or 3. Think of that as being swept out as time progresses up the gamma naught axis. You get to some new gamma I, and the thing that's swept out is a bivector in this space, gamma I wedge gamma naught, and we call that sigma I, and we'll see why that is so in a moment. These type of things square to +1. And of course, the way we've done it, these are actually space-time bivectors, but they can function as spatial vectors in the frame orthogonal to gamma naught. So what we do is call these relative vectors. The relative bit means relative to the velocity vector of the frame. And what you can do is you can take their dot product. Sigma I dot sigma j, I've written that out fully in terms of the anti-commutator, and you get a half into minus gamma I gamma j minus gamma j gamma I, and that is just delta ij. And also, if you did this thing, you took their commutator, which is just here, you find you get epsilon ijk I sigma k, where this is a standard thing from ordinary Cartesian. Epsilon ijk is +1 if it's a positive permutation, -1 otherwise. And of course, these two things here are the defining properties of the Pauli spin matrices. So we've got exactly the same thing happening here. We can think of these as vectors in the space orthogonal to gamma naught, and then we have the Pauli spin matrices being represented by these vectors in exactly the same way as we just had with gammas. Now, a particularly nice feature of this is that if we take sigma 1, sigma 2, sigma 3, which are expressed in terms of the gammas like this, you expand it out, it turns out to give you I. And so the 3D subalgebra shares the same pseudoscalar as space-time, which is very nice. We don't have to have two different symbols for that. So we've got this, therefore, this picture of how the even subalgebra, the STA, sits as a subalgebra, clearly, but sits in this particular relation to the full 4D algebra. So the full 4D algebra contains 8 odd elements, the 4 gamma mu's, the 4 trivectors, and then the rest of it is the even ones, and these come down in this form here to give us the Pauli algebra of 3D. And now the odd things here are the vectors of it, which are the sigma I, viewed from 3D, and the pseudoscalar I, which is odd and viewed in this way in 3D. And so the subalgebra of this that's just even would just be 1 and I sigma I, and that does for us as being the quaternions. Okay, so the next thing we need, if we're going to get further in physics and electromagnetism, we need an additional entity, which is the derivative operator. And we define this via something called the reciprocal frame. This is extremely useful throughout mathematical physics. And what this is if E subscript mu is a frame, the reciprocal frame, E superscript mu, is defined by this. E nu dot E mu is this Kronecker delta, delta mu nu. That's 1 if mu equals nu, 0 otherwise. And note in particular that these are just vectors. They're just like the E mu, but they satisfy this reciprocal relation here. And they, in particular, they don't belong, for example, to a space of 1 forms. You find when you're doing the space-time algebra and geometric algebra generally, that you can understand things written in terms of differential forms, but you don't need separate spaces for them. You can replace them by objects which are just living in exactly the same space that you started with, i.e. the STA. So we can use these reciprocal frames to define the vector differential operator for space-time. That's grad is gamma upstairs mu d by dx mu, and we can write that as gamma mu partial d mu. Now, as a quick encouragement, with just this object, this grad, and the STA, you can basically do all of electromagnetism and quantum mechanics through to electroweak theory without introducing any further new mathematics. And I'll be claiming near the end that that extends all the way through to SU3 and the strong forces. Just a little point here, this is slightly off the main theme, but the definition of grad above, we didn't need to use rectangular coordinates on the orthonormal system gamma mu. Suppose you've got an arbitrary coordinate system, for example, standard polars instead of Cartesian, and then what you do is you let x be the 4D position vector, and you find that the following frames are reciprocal. E downstairs mu is the partial d mu of the position. It turns out then the reciprocal frame is the grad of the nth coordinate. You can show, you might like to try this, that they are indeed reciprocal frames. And then the geometric object grad is given by this E upstairs mu d by d mu in this new system. And that's one extremely useful fact. The other is that the upstairs and downstairs components of any vector are given by dotting your vector A with either E upstairs mu or E downstairs mu. And now, you might think these statements look trivial. They're enough to do everything associated with vector calculus and curvilinear coordinate systems. Just this replaces pages and pages of formulae that for curvilinear systems that you'll see in textbooks. So it's a great saving in time and effort. Now, suppose I want to then look at Lorentz transformations in the STA, and suppose I want to do a Lorentz transformation in the x direction with rapidity parameter alpha. And the way we do that, we think in terms of frames normally. E mu goes to E mu dashed, where E mu dashed we can now represent as R E mu R reverse, where R is this hyperbolic rotor that we saw before. We write that as e to the alpha sigma 1 over 2. And basically, we can generalize this to R equals e to the b, where b is any bivector in our algebra. And the same Rotor prescription works for Lorentz boosts. These are things that have sigma 1s here, sigmas 1, 2, 3, as well as rotations, in which case you would have an I sigma I. And so it's this rotor formulation that provides general Lorentz transformation. It works for any object in the algebra. Any object M, you rotate with M dash is Rm, R reverse. This is very simple. You met the Faraday bivector yesterday. That's written as e to the IB. The I here is a pseudoscalar for space-time. And this gives the electromagnetic field strength. And that just transforms to a new frame as RF, R reverse. Again, you can find formulae which are pages long in some textbooks for this transformation. And it's all contained in this incredibly simple RF, R reverse. Now, what we're going to do now is move off to quantum theory, because I want to get that framework in place before deriving electromagnetism from it, okay? We're going to be treating electromagnetism as a gauge theory, and I've chosen to illustrate how gauge theories worked by deriving electromagnetism from invariance of the Dirac equation. So let's go off to quantum theory next. And basically, the algebraic structure of wave mechanics arises very naturally from the geometric algebra of space-time. It allows us to reformulate standard quantum mechanics in a more geometrical way. It also suggests new lines of interpretation. And we're going to start with Pauli spinors. We've mentioned the Pauli matrices already. Now, actually, they're normally thought of as operators on column vectors, as was mentioned this morning. And the column vectors are the things that are thought of as the Pauli spinors. So the Pauli matrices, they're shown here. They're matrix operators, and they act on two-component Pauli spinors like this. We write them as psi 1, psi 2. These are complex quantities, so there's 4 degrees of freedom. Now, in the GA approach, something quite remarkable happens. You can replace both the objects, that is both the operators and the spinors, by elements of the same algebra. And so space-time objects and relations between them can replace all single particle quantum statements, which is quite dramatic. And the crucial aspect you have to understand is how to model the Pauli-Dirac spinors within STA. And for Pauli spinors, they got 2 complex entries in a column spinor. You put psi 1 is A0 plus IA3, A0 and A3 are 2 constants. You put psi 2 to be minus A2 plus IA1, A0 through A3 real scalars. And then the translation is as shown here, right? So we have this complex thing here, A0 plus IA3 in the top, minus A2 plus IA1 in the bottom. How does that translate through? It's very simple. It's A0 plus AK I sigma K. There's a sum over these Ks, right? So there's 3 of those. And just as an illustration, if you have a spin-up state, denote it plus, that just becomes 1. If you have a spin-down state, you get minus I sigma 2, and then you can get anything else by combinations, effectively, of those. But complex combinations, we'll see what you need to do to get a complex version of this within the STA in a moment. Now, the crucial thing to show this all works is to show that the action of the quantum operators, sigma k hat, on state psi, has a completely equivalent thing as the, in terms of operations on the multivector psi. And here's how it goes. Sigma hat k, so the matrix operating on the state psi, turns out to be the same as the kth sigma on the left, psi, and then a sigma 3 on the right. And you can see that the sigma 3 on the right ensures that sigma k psi sigma 3 always stays in this even subalgebra. So this is, it's double-sided, right? But it preserves the fact that psi is in the even subalgebra. And you can then go ahead and verify the translation procedure is consistent by computation. And here's an example. We act with sigma 1 hat on psi. That permutes things like this. You work out what it translates to. It turns out you can then directly show that sigma 1 psi sigma 3. Okay, so that's a direct computation which verifies this equivalence. Now, I mentioned we need a translation for multiplication by the unit imaginary I, and you can do that by noting that if you multiply the three Pauli matrices together, you get this simple matrix here with just I on the diagonal. So multiplication of both components of psi by I is got by taking the product of these three operators. We can do that. It turns out that gives you psi I with I sigma 3 to the right. Okay, so the role of sort of an uninterpreted complex unit imaginary conventionally is taken over by I sigma 3 to the right. And this is basically David Hessner's found this originally when he was working on the first versions of all this. And this is sort of stuck ever since as being the way to go about having a representation for the act in ordinary quantum mechanics of multiplying by I. And we'll see that this is basically, this thing here turns out to be the origin of electromagnetism, how this operates on the right and what you can do to make the symmetry of this operation of multiplying by a phase become a local one. Now, we can carry on. We can define other things. Let's take psi reverse. In 3D, that's just a scalar. And you can therefore write psi is rho to the half times r, where r is now a rotor, because then psi reverse, if r reverse is 1, is just rho again. So here we can decompose our psi into a rotor and a scale factor. And so now you can begin to see that these spinners people were working with for many years are simply unnormalized rotors. More things we want to do, Hermitian adjoints. It turns out that corresponds to reversion followed by reflection of the time axis in general. That's what happens in the Dirac case. But the reflection of the time axis, we put a gamma naught each side. The gamma naught passes through the Pauli spinners because they're in the even subalgebra. So in 3D, you've got that the Hermitian conjugate is actually just psi reverse. And you can use that to derive the quantum inner product. It turns out that the bra ket put together here, the psi phi, is equivalent to this Hermitian conjugate psi dagger times phi, and you put these angle brackets around. What does that mean here? We aren't doing a Bra-Kent notation. This is just a standard way of representing the scalar part of a quantity in geometric algebra. So you take the scalar part of psi dagger phi, and then you multiply by I sigma 3 on the right, and take the scalar part of that, multiply by I sigma 3, and that's a full translation for the inner product in terms of the STA. So this view, it offers a number of insights. It transforms your view about ordinary quantum mechanics. One can suddenly see what's going on in ordinary quantum mechanics with things like spin precession, things like that, and various ways in which people are using the observables corresponding with spin. You can now see them coming straight out of this rotor approach in an incredibly simple way. But you could have a look at the previous game talk for some examples of that in the 3D case. What we're going to do now is jump straight to the 4D case in Dirac wave functions. And really, we haven't got too much new to do to deal with Dirac theory. So this is the relativistic theory of spin-half particles. And it's very simple. The Dirac wave function now consists of all elements of the even subalgebra of the STA. And so it turns out that when we do that, the wave function is no longer a weighted spatial rotor, it's now a weighted function times a full Lorentz spinner. So here is our psi. We now have 8 components corresponding to the 8 even elements in the STA, and you can always write that as rho to the half, rho is just an ordinary scalar, just like before, times the rho to r, which is now a full Lorentz spinner, and then you get an additional thing, which is e to the I beta over 2, written like that. Beta is a scalar. And so you have a sort of duality rotation coming in via this I factor here. And it must be said, I don't think David Hessner's believes he's ever got to the bottom of what this factor here means. It does seem to be related to antiparticle states, and we can, of course, use it perfectly well in all our computations, but having a feeling as to what it means that's comparable to, say, the rho being the scaling and the r being a rotor, that's basically still for someone to work out, I think. So the main new thing we need to do to make all this work is to establish what the action of the Dirac gamma matrices are on a state psi. So we want to know what gamma mu hat, where that's a matrix, translates to. And here's the answer. It's double-sided again. We now get gamma mu on the left, that's one of our STA vectors, times psi times gamma naught. And the gamma naught on the right keeps this in the even subalgebra. It turns out that the imaginary is the same as in the Pauli case. It's still I sigma 3 to the right. That persists all the way through. And now you can start forming observables, and these are things that basically are bilinear operations on the psi. The most useful one of them all is what we call J, the direct current. That's formed by psi, gamma naught, psi reverse. If you take that form of psi we had just now, in terms of the rho e to the I beta r, then you'll see that this thing here, because I should say I anti-commutes with gamma naught, but reverses to itself, try it out, put psi equal to psi times e to the I beta over 2, you'll see that you lose that mysterious e to the I beta factor completely, and you just get that J is rho times R gamma naught R reverse. Exactly the same thing happens for transforming gamma 3. We think of that as a spin vector, and that's rho gamma 3 R reverse. And we get this quite nice picture, which is very similar to rigid body mechanics, of how you start off with your fiducial gamma vectors. Psi then transforms these to the observable J equals rho V, the spin vector S, and then 2 more things, and these represent phase. They get rotated round by phase changes I sigma 3. Now, there's our wave function. What is the equation it obeys? And it's incredibly simple. This is the form first proposed by David Hessner. This is for free space. And you get grad psi I sigma 3 to the right is m psi gamma naught. And it'd be hard to think of anything simpler that you could write down that's obviously got to combine the geometric algebra grad, just here, the geometric algebra psi, and bring in the mass m. Anyway, that is the equation. That is the full Dirac equation in free space. And if you now form the divergence of J and use the J as psi gamma naught psi reverse, then you're going to get terms in grad psi. You use what grad psi is from this equation just here. It's minus m psi I gamma 3 when you move that over the other side. And it turns out then that you can quickly find you get 0. So the divergence of J is 0. The current J is conserved. And that has the implication that fermions cannot be created or destroyed. And basically, pair annihilation and production are high-energy multiparticle processes. They're not covered by the Dirac equation in this form, right? So everything I'm talking about in regard to quantum mechanics here is all at what they call the first quantized level. To cover these sort of processes, you'd have to go to second quantized systems, which we believe you could do via a multi-particle version of the Dirac equation, but we never got through to the end of that in terms of having a fully working system. That's still to be done. Now, something I want to help emphasize here is that the time-like component of J is positive definite. So explicitly, if you use later, I want you to see that gamma naught dot J is gamma naught psi reverse. I put it in this angle bracket thing to indicate taking the scalar part. And it's the sum of 8 squares, and the 8 squares are the coefficients that we introduced earlier to describe the state. Okay, so gamma naught dot J is an sum of 8 squares. And it's clearly positive. That's a key thing there. It's interpreted as a probability density, and a normalized wave function has that the sum over space of J naught is 1. And conservation of J then means that you can think of probability density flowing along non-intersecting streamlines. And I'll do this very quickly, but I know some of you will have seen this before. This is the first, this is a first application of this particular apparatus that we've built up so far to visualizing what's going on in a quantum so-called measurement. What we're going to look at very briefly is Stern-Gerlach apparatus. This is where you've got a field in this direction, particles passing through it, electrons passing through it, for example, well, something which has spin, and it is separated out into spin-up and spin-down components. And in the traditional view, what you're doing is measuring. The view we would have via the development so far is that the apparatus acts as a spin polarizer, forcing the spins to align with the magnetic shock of going through this region. And this shows a case with an initial wave packet, which is a Gaussian in the z direction. It gets split into these two packets here, and you can see the streamlines, again, show this splitting, they bifurcate. But the key thing is this one, which is for the spins. The spins are all in the x direction when they go in. They get churned up by the magnetic fields, but then as they spread out from the apparatus, they all gradually turn into either completely up or completely down. So you've generated a spin up or spin down bifurcation, but you've done it in this sort of rather causal, deterministic way. So where does the randomness come in? That comes in where in the wave packet a particular streamline is seeded. One's near one side of it will go one way, one's near the other side of it will go the other way. And so you replace questions about collapsal wave functions, things of that kind, by asking, well, what's the initial data you have? And once you've got presumably randomized initial data, that can feed through to the end of the process to give you the standard quantum mechanical predictions, but you've been able to maintain a causal deterministic picture throughout of what is happening. Okay, now let's get on with our forces, and I want to look at electromagnetism as a gauge theory, because that provides a very straightforward way to understand a process which applies, as we'll see, equally in gravity, weak interactions, and strong interactions. So we're going to start with the Dirac equation. And since I sigma 3 and gamma naught commute, you can put an extra I sigma 3 component, let's do it as e to the I sigma 3 theta, through on the right-hand side of this. It can commute through, and you will get a symmetry of the equation. Clearly, if psi dash is this rotated wave function, rotated by an e to the I sigma 3 theta on the right, then psi dashed is a solution of the same Dirac equation. But what if your theta is a function of position, x, and what you find when you calculate grad of psi dashed is you've got an unfortunate extra term, a grad theta times psi Ri sigma 3 on the right-hand side, which spoils the covariance of the equation. What we're looking for here is an operator that can replace the grad to give you something covariant where solutions remain solutions after this rotation. So at the moment, the phase rotation does not work as a local symmetry. Why should we want it to? Basically from the structure of physical statements in the Dirac theory. And these are of two main types. You've got observables, such the JS that I brought in, they're bilinear and psi, or you've got simple statements of equality, like psi is psi1 plus psi2. Now, both of those remain locally invariant. I can put in an e to the I sigma 3 times theta, where theta is a function of position, and both of those things would survive that, and they would still give you the same value observable or the same statement of equality between spinors. So it's only the derivative which has got a problem. So you've got to change the grad operator to get rid of unwanted terms and the gradient of R. Now, I'm going to express the results here in terms of just one further bit of notation, which is what we call the multi-vector derivative with respect to A. And basically, if A is a vector, A upstairs mu, E downstairs mu, then this dA is just like we had earlier for the gradient. It's E upstairs mu, D by dA mu. You can see that dx, or x position, would just be the same as grad, but we can take derivatives with respect to any vector. And it's got these rather nice properties here. There's one I'll highlight at this point, that dA differentiating A through an R grade object returns this thing, -1 to the R, n minus 2R, AR. N is the dimension of the space, R the grade of the object. So you'll notice that if you differentiate through a bivector in space-time, so n is 4, R is 2, you get 0. And it turns out, I mean, it's of course not obvious, this turns out to be key to why electromagnetism is a massless theory in 4D, and also one can use it to demonstrate how the Riemann tensor for a black hole works and gives a solution in gravity. Okay, so we can write our equation for grad psi dashed like this. Here we've taken d by dA of A dot grad, that's just a way of reassembling the grad, and psi times A dot grad of R. And it's the last term which is doing the damage. So we define a new operator like this. We define it as the original one, but plus 1/2 psi, and then we put something to the right of psi, omega of A, and we're going to figure out what omega of A has to be to make this work. And we want a new Dirac equation which employs this covariant derivative on the left-hand side. So let's actually carry out psi dashed equals psi r. So you'll have d goes to d dash. D dash should have the same form as d. And so for d dash, we're going to write it like this, where the omega is transformed to an omega dashed in such a way as to make everything work. And what you'll find pretty quickly if you go through this is that you need omega dashed to be r reverse omega of A r minus 2 R reverse A dot grad of R. So this bit here is going to be of exactly the same form as the original omega, so it's just a rotated version. It's this new bit here which tells us what type of object we've got. And we can find out by differentiating R reverse R equals 1. Let's differentiate that with A dot grad. Then you get A dot grad R reverse R plus R reverse A dot grad of R equals 0, because 1 differentiated gives 0. And we see this bit here is the same as this. If you look at this line here, then you've got the thing we're interested in. When it's reversed, which is what's happening here, gives minus itself. So it has to be a bivector. So we've established that this thing that has to sit, I'll just go back, the thing that has to sit here in this covariant derivative has got to be a bivector function of A. It's called a connection, and technically you can think of it as belonging to the Lie algebra of the symmetry group, but we'll have more to say about that later. And in general, omega of A will not be expressible as a derivative of rota, and this is the essence of the gauging step, right? You take something arising from a derivative and generalize it to a term that cannot be formed this way, and we'll have a concrete example of that in a moment. So all of that was for a general rota R on the right-hand side of the wave function. And in fact, that's just done half of gravity for us. Okay, not just electromagnetism, but half of gravity. To get electromagnetism, we now restrict the rota to the form we first thought of with this phase change, e to the I sigma 3 theta. So let's work out what this is. Here's the object. The new bit is minus 2 I reverse A dot grad R. I won't go through the details. It's pretty quick, but you find that that's the same as A dot grad theta I sigma 3. And so this is the gauging step now. We've achieved this bit via derivative, A dot grad theta. What we do now is we generalize the form of this to a new object. And you can see we could do that if instead of a grad of a scalar, we put a general vector in that position. And that general vector is the four potential of electromagnetism, A. And we bring in a coupling constant at the same time. We call it lambda here, to write that omega A, this connection, is lambda A dot big A I sigma 3. And you can see that is indeed a bivector because it's I sigma 3, and it's a linear function of A. And under gauge transformations, the gauge field A must transform like this, right? And we would get no result from the curl of A. So curl of A would be 0 if we had it just as a grad theta, because the curl, and that is grad wedge, of grad theta involves a grad wedge grad, which they're parallel, if you like, and so, of course, you get 0. So it's only when curl of A is non-zero that you're going to get any genuine physical effects. The rest are gauge effects. So piecing that through, you put this new term in the equation, and you get this. Grad psi I sigma 3 minus EA psi, this is a new version of the coupling constant, is M psi gamma naught. And there we've got the Dirac equation with electromagnetism. Now, I've said that there's real physical effects when the curl of A is non-zero. How can I say that? Well, the next thing in a gauge theory is to work out the commutator of the covariant derivatives, because that's how you get physical things. And let's do it again. Let's go back to psi goes to psi r. If A and B are constant vectors, then you can work out the commutator dA dB acting on a general psi for these rotors at the right, and you find that all derivatives of psi cancel in this, and you get this thing over here to the right of psi, A dot grad omega B minus B dot grad omega A minus omega A cross omega B, in which all the derivatives of psi have cancelled. And that's the general result, which we'll see in a moment in gravity. But let's now restrict it back to this form that we have when we just got a phase term. And we know that omega of A is that. You put it in here. This bit here, the commutator of omega A cross omega B, that vanishes because it's just an I sigma 3 commuted with I sigma 3. So that's not going to give anything. And that corresponds to electromagnetism being what's called an abelian theory, where these bits of the connection cancel, and you're only left with this gradient bit here. You work out the gradient bit, and you find that it's equal to A wedge B dot F, where F is the curl of A, times I sigma 3. And so the conventional thing that we now do is we forget this is actually a mapping, an omega of A. We strip off the I sigma 3, and we think of F itself as being the field strength tensor. And of course, as we've said, it vanishes if A is pure gauge. If A is grad phi, it just vanishes. Now, to get all the way through to the Maxwell equations, then you need to write down a Lagrangian for your system, and that's incredibly simple. It's just minus half f dot f minus a dot j, where j is some external current. And you work out the Euler-Lagrange equations for this. You get grad f equals j, which, as you saw yesterday, is the full Maxwell equations. And you can get the usual four Maxwell equations if you write f equals e plus ib. So that's showing us how electromagnetism, we now have all the equations of it, emerges from the requirement to preserve phase invariance under local transformations. Okay, let's get to gravity. And so in gravity, we'll want to do something that is going to be as much as possible like the other three forces of nature. And we know all of these are described in terms of gauge theories. They're of a type, this business of the local scaling giving us a connection is called the Yang-Mills type gauge theory. And they're all in a flat space-time background. And so in the same way, gauge theory gravity is expressed in a flat space-time. The key question is then what we're gauging. And we choose this to be Lorentz rotations at a point, and the ability to carry out an arbitrary remapping from one space-time point to another. So this is rotations, in the Lorentz sense, and translations. They're the key things that we're going to be gauging. And again, it's much easier to work with the Dirac wave function as your starting point for this. And in fact, as I said, we're quite lucky because in the electromagnetic derivation, we've effectively already done the first of these, except we now want rotor transformations on the left of the wave function instead of on the right, because this is how the wave function responds to actual space-time Lorentz transformations. The R appears on the left, not the right. The things on the right, like the phase, are internal transformations of the system. On the left, they're responding to space-time transformations. Now, for the second, I won't go into the details of this, which was the arbitrary remapping of one space-time point for another, because thinking of it that it's translations, it's got a vector type appearance instead of a bivector type appearance, and you find you need a vector field, which is a linear function of some arbitrary vector A. Now, I won't go into the details of this. I'll just show you very briefly a couple of examples of this. And again, as before, we get the field strength tensor by commuting the covariant derivatives. Here we commute them for the Lorentz field. And what you find is that, again, all the derivatives cancel out, and you get, applying this to some arbitrary multivector M, you get what is, in fact, the Riemann tensor cross M. And here it is spelled out again. We've seen exactly this form from what we did before. That is the Riemann tensor. And it turns out you can make a fully covariant version, which is then invariant under the translations as well by writing this curly R of B is RHB. So we stick in an H, that makes it fully covariant. And this is a bivector function of bivectors. You can see the output as a bivector. And it's just like the inertia tensor, as Leo was just, of the type Leo was talking about before. It's a mapping of bivectors to bivectors. And then you can set up what you need for your Lagrangian. And for that, you take dB wedge dA dot of the Riemann tensor. That gives you a scalar. And the simplest gravitational action you can use, this corresponds to what's called the Einstein-Hilbert action, and was how general relativity was first derived as via Lagrangian, like this. You take the determinant of this vector function H multiplied by R. And that's it, basically. We first did this back in the 90s, and there's a full description in this paper here. What theory do you get in this way? Well, basically, it reproduces the predictions of an extension of general relativity known as the Einstein-Cartan theory, which incorporates quantum spin. You can see that's going to happen because we started with the Dirac equations. So, of course, we're going to be able to incorporate spin. But basically, because it works in this gauge theory sense in a flat background space-time, it differs on global issues such as nature of the horizons and topology. A big advantage is that you can be very clear what the physical predictions of the theory are, since it's a gauge theory, and the physical predictions are those that are gauge invariant. I've already said it's conceptually simpler than standard GR, since it works in a flat space background, and I think it's very important that in a practical sense, if you have a Clifford algebra program that can do, a computer algebra program that can do Clifford algebra in space-time, then you can immediately start exploring gravity. You don't need tensor calculus or any extension to curved space. You can do all of the gravity that you need just with this. And again, to emphasize the simplicity, in the absence of matter, here are the equations. It's dr of this Riemann tensor equals 0. This is a full Clifford product here, so it's got both trivector and vector parts. And the curl of this translation field is 0. Now, I'm going to give just one example of how things look in this, which is taken from the set of 3 that I looked at last time. And basically just want to say, how do black holes look in this approach? And it becomes exactly like you would do in electromagnetism when you're setting up equations for a point charge. You need to choose a gauge and work from there. And the gauge here, we're going to do it in terms of a choice of H function. We want to cover all of flat space, except, of course, possibly a singularity at the origin. And just like in electromagnetism, where you choose different gauges, you'd expect the field strength tensor to be the same and not to depend on the choice of gauge. Well, how does that work out? Going to have ER as the unit radial vector, ET equals gamma naught as the unit time vector, and you can then define a radial null vector, which we need in one of these forms, as E minus equals ET minus ER. You can see that's null. And then here's 2 good choices for this H function. The first we call the Newtonian gauge. A lot of the physics looks very Newtonian-like in this gauge. And we have H of A as A minus the square root of 2 ohm over R, A dot ER ET. Pretty simple. And then there's another type. I wanted 2 gauges, so I can show you they lead to the same Riemann tensor. A plus M over R, A dot E minus E minus. This is the gauge theory gravity analog of the advanced Eddington-Finkelstein metric, and is very good for treating the paths of null things like photons. If you work out the Riemann tensor from those, they both give this form here. R of B is minus M over 2R cubed, B plus 3 sigma R, B sigma R. And you can see that this is going to return you a bivector, because here we've just got the bivector coming back, but here we've sandwiched it in sigma R. That's going to give you another bivector. So it is indeed a mapping of bivectors. And you can immediately check this field equation I talked about. Using the results for the dA derivative above, then you should have a look through this, and you'll see that you take dA of, for this bit, A wedge B, and for this bit, 3 sigma R, A wedge B, AR. And you unwrap it so you've got explicit A's here, and you can see this bit here, dA sigma R A is going to return 0 from what I said earlier. And you get 0. So this is really very impressive as regards to compactness and ease of working. Now, just to finish on the gravity bit, is the correct theory of gravity just based on local invariance under rotations and translations it, or is there more? And I personally think that we want to bring in further invariance, that is scale invariance, the ability to carry out an arbitrary rescaling of lengths at each point, that this should be a further invariance of gravity. So we can rotate, we can translate. What's the other thing that we might want to take from conformal transformations that's a continuous thing you can do at that scale invariance. And with colleagues, we've now developed a new theory of gravity where all the elements of the Lagrangian are indeed invariant under scale changes. And you find that this means you've got to include what's called torsion. This is a bivector valued function of position. It's not a new field. It's part of the connection we already talked about. But where it shows up is it modifies this curl of H equals 0 equation to this. Curl of H is now S of H of A, where S of A is this torsion. And the torsion and the scale invariant nature of the theory, we believe, is actually crucial in understanding the origin of the cosmological constant. You've probably heard many times that the cosmological constant is one of the most glaring problems in physics. If you think it's provided or comes from, the cosmological constant is meant to drive the expansion of the universe at the moment, makes it accelerate. And where's that coming from? It could be vacuum energy, but if you work out the vacuum energy that you would get if you interpreted it naively from particle physics effects, so the sort of boiling vacuum of particles being created and destroyed, it turns out it's about 10 to the power 122 times bigger than the actual cosmological constant, which we now observe. And so it's very hard to see how that could be a good explanation. But you find in this approach here that if you have a constant time-like torsion of this form here, so the bivector field S of the vector A is A dot I gamma naught, right? This is a trivector, so A dot that is a bivector. Q naught's just some scalar constant. This can provide a late-time dynamical effect in cosmology, which precisely mimics the external vacuum energy. And you find also that as the universe develops, it does actually go to having this type of torsion at late times by itself. So there's a couple of papers you could look at here which explains this. Unfortunately, for current purposes, both of these are written in conventional notation, but you will find in the second one here a section written in GA which explains all the different types of Lagrangians that we combine to get scale invariance. So all the possible scale invariant ones, there's about 6 of them, are put into this theory. And that's explained there in GA terms. Right, now I get, now I get to octonians. So is everyone brave enough to carry on at this point? Okay, right, so let's say some things about octonians generally to start with. So they were first introduced as a generalization of quaternions by Graves in 1843 and Cayley in 1845. Now, I say that Graves introduced them in 1843. Unfortunately, his first actual paper concerning them wasn't published till just after Cayley's paper in 1845, but he's generally given credit for coming up with the idea first. And I find it rather amusing in its way to look at both these initial papers. Here's the start of Graves' paper, published in, basically it was the Philosophical Magazine of the Royal Society. And it's about the connection between the general theory of normal couples and the theory of complete quadratic functions of 2 variables. Neither of those are anything to do with octonians. And it was, the octonians were only mentioned in a PS to the article. And here is his PS, which is expressing how he thought of them. And he thought the most important thing was this theorem here. The product of 2 sums of 8 squares is a sum of 8 squares, which he had managed to prove in terms of these new numbers, the octonians. And we'll come back to this theorem below. And it's also interesting, the slightly earlier paper by Cayley in 1845 was about the quite different subject of elliptic functions, with the octonians only occupying a postscript, right? So they did things differently in those days. You could put in postscripts on some totally new thing, and it would be fine. As we've already said, the key features of octonions is that they form a norm division algebra. Any product of octonions has a norm which is a product of the individual norms. And two non-zero octonions always multiply to produce a further non-zero octonion. And the only norm division algebras are complex numbers, quaternions, and octonions. And I've already said this, that the octonions have this feature that they're neither commutative nor associative. And so in particular, there's no general rule that AB times C is the same as A times BC. And it differs, of course, fundamentally from the geometric product of GA in this regard. So how is it that they could be useful in physics, and how we're going to be able to represent them within GA? We're going to use the STA. The key is that in the STA, Dirac spinner's psi can be divided into parts that commute or anticommute with the unit time vector gamma naught. So basically, the sigmas and the I that we had before, so 3 sigmas and I, they anticommute with gamma naught. And the Pauli parts, the scalar and the I sigma I, they commute. And so what we're going to do is, for a general psi, we're going to define the even part, psi plus, as a half psi plus gamma naught psi gamma naught, and the odd part is a half psi minus gamma naught psi gamma naught. And these correspond to the even and odd parts of the full Pauli algebra. And here it is. Here's the answer then for how we multiply two octonions, psi and phi, which to us are Dirac spinners, to get a new Dirac spinner which has the properties we need. It's to do this. We're going to call the operation of octonionic multiplication star, and the new spinner is given by this. It's the product of the even bits. Then we have phi reverse odd part times psi odd part plus phi odd psi even plus psi odd reverse of psi plus. That turns out to give us the full octonion multiplication. And you should note carefully that the 4 individual products here, they're all usual geometric products taking place within the ordinary STA, and the reverse here is just an ordinary STA reverse, and the spinners are just ordinary STA spinners. Hence our claim about being able to compute everything entirely within the STA. Now, from the form of this, you can see such a product is highly unlikely to be associative. Indeed, in general, it's not. The property it does have comes from essentially the defining property of the octonions, that they form a norm division algebra. Now, we need the norm, so we need to define a conjugate element which we can multiply in to get the norm. So we're going to use star to denote conjugation, and it works like this. Psi star is the reverse of the even part of psi minus the odd part of psi. And just with that, and our definition of the product, you then find the following norm. The norm of psi, which is psi octonion product with the octonion conjugate, turns out to be this. It's a half gamma naught psi reverse plus psi gamma naught psi reverse gamma naught, which I'll recognize as the Dirac current, okay? Which is extremely intriguing. And we can see this makes perfect sense as follows. We know from its interpretation as a probability current that J is always non-zero and future pointing as long as psi is non-zero. So this thing here is always going to be positive, which you need for a norm. And it's a scalar, and so it coincides perfectly with the properties a norm should have. Well, there's one more property we need to verify. That is that the norm of a product is the product of the norms. Okay? It's got to respect multiplication. And so here we have the norm of psi producted with phi should be this product of norms there for all Dirac spinors psi and phi. And given our definitions so far, this is a matter of computation, right? We just work this out within the STA and see if it works. And it does, okay? So we have indeed instantiated this norm product. And given our reinterpretation of the octonionic norm in terms of direct current, you can see with theta as being the product, it corresponds to this ordinary STA result that theta gamma naught theta reverse dot gamma naught is the individual, it's the product of these individual direct currents, time-like components just there. And now we can make contact with that PS of Graves, because we've emphasized earlier that the direct current is the sum of 8 squares. If you remember, the A0 squared plus A1 squared through to B3 squared. And so this is a sum of 8 squares, this is a sum of 8 squares, and what we're saying is that their product is indeed another sum of 8 squares, which is very nice. And I find it quite startling that Graves could write down something in 1845 about the product of 8 squares product of 2 sums of 8 squares is a sum of 8 squares. And suddenly we find out 150 years later, basically, that that is telling us something profound about the direct current. Okay. Now, here's what the multiplication table for the octonions looks like in a particular form. Unfortunately, you can have multiple forms that are possible. This is what I've given you here is the one corresponding to the influential review of octonions by Baez, and is also that used by Cole Fury, who I mentioned earlier. And I'm going to refer to some papers as we go along. I've got references all at the end, so they'll all be visible at the end of the talk. And this table, unfortunately, is just one of 480 that you can use, so there's another 479 possibilities. It's better not to look at this table, but to look at the Fano plane representation of octonion multiplication. And just look at, first of all, at the things on the left-hand side of each assignment. So there's E6, E4, E7. These are the octonions which are not E0. E0 is just 1, we can think of it. It squares to itself, all right? Go down that diagonal. It squares to itself, and the E1 squared gives minus E0, E2 squared gives minus E0. So all these things here, they're like generalized quaternions in that they all square to -1. And indeed, the first part of the table you can think of as a quaternionic table, but then we extend them with these extra bits. And this is a mnemonic for being able to figure out how to multiply them. If you follow the arrows, E6 times E1 gives you E5, and the same for all the other arrows around here. Now, how do we assign these to STA elements? Well, I've done it here in such a way that the pseudoscalar, which I feel is distinguished, is in the middle here at E7, and then these three at the midpoints are the I sigma 1, I sigma 2, I sigma 3, and the ones out here are the sigmas. So that's how I've chosen to set up the correspondence with the STA. Now, we've already said that fundamental forces appear to work via localization of global symmetries. This introduces new forces, and the way of introducing new fields which give the forces is the same for electromagnetic weak and strong forces. Go via this procedure I've already shown you with the connection, and the Lorentz rotation part of gravity. So we already know how to do all that bit entirely within the STA. So the starting point for understanding a force now, because we don't need to worry about the gauging aspect, that's all clear, is to identify the global symmetry we think should be obeyed. And the best way to express this is via a group. There are a lot of groups. How do we or nature pick out the ones which are relevant? And what we would like to move towards is understanding the gauge groups at the heart of the standard model of particle physics. This is what they are. it appears to work with a direct product of groups SU3 cross SU2 cross U1. And can we find these emerging from some general principle? Well, here I want to look at what octonions have to offer in this direction. And as I say, this is going to be following what Cole-Fury and others have particularly emphasized as regards the role of chains of octonion operators. And this is a clever technique where you use sequences of octonions to pack in a great deal of information despite the relatively small size of the spaces involved. And here, the non-associativity of the octonions is crucial since, okay, suppose we have a chain with B, so we take phi times B multiplied at the left, and then we use A as the next thing in the chain. That does not have to be the same as AB acting on phi, because the lack of associativity. So having no associativity is actually a benefit here because we can start building up some complex chains which are not just the same as piling everything together. This process does not go on forever, and you find that 7 left multiplications or 7 right multiplications, if you're doing it on the right, is the maximum you need to consider. And that means that if you consider purely left multiplications, then you can consider sequences with a maximum of 6 of these, and Fury and others show that this is isomorphic to the 6-dimensional Clifford algebra CL06. It's got 6 grade 1 objects squaring to -1, and so we call that anti-Euclidean Clifford algebra. Now, maybe I should skip a bit here, because I really don't want to go on far too long, but the fact that we can have something isomorphic to a Clifford algebra, we can understand quite well from the STA viewpoint. Basically, what we need to do is show that if we have a chain, EJ times phi, and we do another thing with an EI, that's the same as minus EJ times EI phi, where this is when I is not equal to J. And if we had the same I or J, we'd want this to give minus phi. So I've got this here. Yes, this will do. EI star EJ star phi should be minus phi equals J, and minus EJ star EI phi for I not equal to J. Now I hope you can see there that we've encoded the basis elements of a Clifford algebra with this signature of 6 minor signs. All right, so this, we can define a vector as a map, phi goes to EI star phi, and then we've got the defining relations for unit vectors in the Clifford algebra. And of course, we know that each of these multiplications can be done just in the STA. And so each of these things is a defined map of an STA even grade element to new spinor. And the definition, that's because the definition of the map can be written down entirely in the STA. So what we've achieved is by a 4D Clifford algebra acting on itself, i.e. the STA with a total of 16 elements, we've generated a 6D Clifford algebra with 64 elements. And this is exciting because it's big enough to encompass the entire standard model of particle physics. Right? So let's look briefly at the standard model. So you probably know most of this already, but here are, on this side, the fermions. These are spin half things over here, and they're divided into the quarks, of which there are 6, and leptons, of which there are 6. Basically, you should look down a column here. Look at the column 1. This is called the first generation of particles. We have up and down quarks, the electron and the electron neutrino. Second generation, charm and strange quarks, muon neutrino. And then top and bottom quarks, tau and tau neutrino. So that's all, as it were, the particles. On this side, we have the force carriers, which consists of the gluons, which mediate the strong interactions between these quarks, the photon, for electromagnetism, and the Z and W, which go with the weak interaction, and then the Higgs, which, as you've, I'm sure, heard about, effectively gives mass to several of the otherwise massless particles in the standard model. The thing I'll draw your attention to here, this is a count of all the particles. The gluons work by exchanging colors. This isn't a good word. We arbitrarily assign colors to the quarks. So each of these here, so this up quark comes in 3 different colors, red, green, and blue. They're just labels, right? They don't actually mean anything in terms of colors. And there's also an anti-quark, an anti-up. And so if you just want to consider the up quark, you've got 6 objects, okay? The 3 colors and then the anti-version of it. The gluons, it turns out there's 8 of them. And basically, I've got a numbering here which shows you, right? So we had 2 types of quarks, up-down type, multiplied by the 3 generations. Each has 3 colors, so you get 36 for them. There's 12 leptons, and then for the forces, you can go down this list, add it all up, you get 61 particles. And so people have been definitely very interested in the idea that the Clifford algebra, CL06, which has 64 elements, could be able to represent all the particle states that we need in the standard model. And with a little room to spare, but not too much. So there's not too much room for any extra particles in this. And indeed, Gording and May, in an article actually in Advances in Applying Clifford Algebras, do this. But unfortunately, they do it entirely in terms of 8-by-8 complex matrix representations of CL06. And it makes it very difficult to link up to a geometrical approach. So what can we do in terms of using what we've already got to represent these particles? And what I'm going to do is just take a small part of the structure to show how things work in the STA approach. And basically, what we're going to show is that for the strong force, which is carried by these gluons and which glue the quarks together to form the protons, neutrons, and various mesons of particle physics, the underlying group is SU3, and we're going to understand that in terms of what we've got with octonions. So let's see what. Yes. Okay. So what does SU3 mean? Let's just get clear on that. The unitary bit means that in matrix terms, U times its complex conjugate transpose is 1. And the special unitary group is that you eliminate 1 degree of freedom by demanding that the determinant of the matrices, when you're doing it in matrix terms, is equal to 1, right? So we have 8 possibilities. We've got 3-by-3 complex, gives us 9, and we take out one of the states by asking that the determinant is 1. So there are 8 such states within SU3. And in particle physics terms, these are the 8 gluons we were just talking about. So all that's how it be viewed standardly. Now here comes the bit which is not just standard particle physics. We're going to embed SU3 within a larger group. It's going to be the exceptional Lie group G2. And so we need to know what exceptional Lie groups are. And these stand outside the normal classification groups into an infinite series of 4 different types. And you'll be familiar with some of these. The 4 different types are A, N, B, N, C, N, D, N. And you could have N equals all the way up to infinity. And 2 of them, which I recognize, I think most people would, are the alternating groups AN or the dihedral groups GN. But there are 5 groups which stand outside that classification. And they're shown in bold on this diagram. Sorry, this is a bit complex. But these ones here, E8, E7,
E6, F4, and then we zoom over here, and we get to G2. These are the exceptional groups in the Lie classification, and they're all finite in terms of dimension, and they, as I say, stand outside of this classification in terms of the infinite series of other groups. G2 is the smallest of them. It's got 14 dimensions, and as you may be able to see here, these lines indicate subgroups. It's got SU3 as a subgroup. And what we're going to do, we're going to use the extra dimensions of G2 relative to SU3 to accommodate a quark. We've said that comes in 3 colors. Each has an antiparticle. So for a single quark, we need 6 states. And this works because G2 is 14-dimensional, SU3 is 8-dimensional. Now, possibly, this is all part of a grander scheme. And just an example of that, if you look near the top here, standing pretty near the top is SU8. It's a subgroup. You come out of E8 down to E7 and then to SU8. And this thing, I've now got working completely satisfactorily within these octonionic chains, i.e. within the STA. And so it is possible that we can go much higher up this chain and maybe all the way to E8. It's quite a way. This SU8, which is now completely decoded using this, it stands quite near the top. It's got 63 dimensions, which is, again, quite nice for the standard model. But if we went all the way to E8, that's 248 dimensions, and E7 is 133 dimensions. So clearly, it's not going to fit into just what we've got at the moment. Anyway, just want to say that in terms of SU8, that's it's got a rank. Sorry, this is going to probably attempting to get in too much quite at this point, but the rank of a group, like in G2, the subscript is the rank. In terms of E8, the 8 is the rank. What does it mean? It means the number of mutually commuting vectors. All right, so it's a maximal set of mutually commuting objects. In this SU8 thing, here's the maximal commuting set expressed in terms of these octonionic chains, right? This is completely explicit. Each of these, it is commuting with all the others. Now, quite remarkably, I mean, I played with these for a long while. I eventually figured out what they were when you translate them through to the STA. They're incredibly simple. These are reflection in gamma naught, reflection in gamma 1, gamma 2, gamma 3, sigma 3, sigma 2, and sigma 1, right? Which is incredible to find something that simple underlying something apparently so complex. And you can see immediately why they intercommute, because although, say, gamma 1 does not commute with gamma 2, if you do it each side, you get 2 sign changes, and then it does commute. I'll skip that. This is a nice picture of what's called the root system of E8, showing the incredible complexity of these objects when you get up to these higher dimensions. Rather amusingly, this was done with actual pins and threads. Someone had made this version out of cotton and pins, but it's very beautiful. Okay, we're going to just stick for this final bit with much more humble things. We're going to deal with SU3, which has 8 gluons, 1 quark and 1 antiquark, and we're going to understand how we get this in terms of G2. And it's just going to be what we said. We're going to use something that preserves the time-like portion of the Dirac current, because we have to preserve the octonionic norm. That's the same as preserving the time-like component here. And you get SU3 by restricting this psi here to being just the bivector f, right? Psi is a bivector plus a pseudoscalar plus a scalar. We're going to pull out the f bit and ask what would preserve that. And you can read off some of the transformations by eye. So consider So let's just put F here. Suppose I did a double-sided rotation, R reverse, where R commutes with gamma naught. You can see straight away from this, the R will pass through the gamma naughts, and you'll get something that is just invariant. So such rotors are the spatial rotors, forms a 3-parameter set, and accounts for 3 of the SU3 generators. That's straightforward. There's another 3-parameter set, Fij, that looks like this in terms of the transformation. And then to complete the set, there are 3 generators, Ji, that work like this. X of alpha Jif as an operator is cos alpha f plus sine alpha I sigma I f sigma I. So you reflect in that and multiply by I. And that gives you 3 lots of 3. And the restriction that brings it down from U3 to SU3 is that this sum has to be 0. And what I invite you to do, when you've got the slides, is demonstrate that these transformations I've just told you actually really do preserve gamma naught F gamma naught. And if you do this, you'll be able to understand the finite rather than infinitesimal forms of the SU3 transformations. And you do it just by fairly simple manipulations in the space-time algebra. And doing that with the finite forms we've considered really quite advanced in the usual matrix approach. And then you ask, what are the obvious next things to do as regards gamma naught psi, gamma naught psi reverse? Let's put psi to be the remaining bits. There'll be e to the I beta type transformations. That's your global U1 for the next group that you find within the standard model. Or you could use single-sided rotor transformations of psi, like psi goes to psi r, just like we did earlier, where r needs to be a spatial rotor and commutes with gamma naught, that's SU2. So you can read this off as obvious things and find that structure. Now, finally, what about getting the quarks and representing the whole thing? That comes from identifying some operators here, of which there are 21, called JMN, where M is 1, 2, 3, N is 1 to 7. This corresponds to the set of octonian imaginaries. And this here is the dimension of a set of things that are all mutually commuting. For a given n, all these JMNs are mutually commuting. And it turns out you can more or less directly write them down. You remember that E6 had the STA equivalent sigma 2. You find that you combine these reflections we already had, which I talked about just now, with sigma 2. And you get these things. And it's obvious how these mutually intercommute, because reflections always commute. And then you've got a sigma 2 outside, which also commutes. So using them, you then define 7 objects here, which are differences of 2 of them, and another 7 objects, which are differences with respect to the third one here. And it turns out that the first 7 here are SU3 generators, and M7, the last one of those, is the missing 8th generator, and the MI for I from 1 to 6 are the quark states. And you can immediately identify these things with the Gell-Mann matrices, which people use to do the SU3, and you can put the others together to get the quarks in this form here. The red, green, and blue quarks are these pairs of quantities here. You have M3, M1, and then the antiparticle is M3 and minus M1. And how do the gluons, which are these things here, these are the 8 gluons, how do they interact with the particles? They just operate on them directly via the usual GA product. So what you find, sorry, I rushed that bit because I really do want to finish. I'm sure you do as well. But this gives a complete mapping of the color force and some of the particles it's operating on. This quark with all 3 colors and its antiparticle. And you'll see that you've got 7 plus 7, which is 14 dimensions, and that turns out to be exactly this group, G2, that is the lowest exceptional group. So I'm currently seeking to find the best way of incorporating SU2 weak forces, and hopefully this will look as simple as the above in STA terms. You saw that when we got to the crucial quantities, there was a real pattern to what the STA equivalents looked like, and in particular, the mutually commuting objects, they all worked via reflections, which was very clever. Right, so basically what's particularly nice about what we've got so far is that anyone has a computer algebra program which can do the space-time algebra. And you can do that, for example, if you can do the conformal geometric algebra of 2D space, they can now do the octonions as abstract entities, and they're a lot of fun. Or you can explore the color force between quarks. And I hope to get further in the sense of having much more concrete examples that everyone can try out and encompassing more of the particles and more of the forces soon. So there's some last bits here about some problems that we need to sort through and get right and ideas for future work, but I'm going to skip that now. You can see them at a later time. Thank you very much.
Thank you for this great talk. I have loads of questions, but maybe I should just pick the most important one that jumps out at me. I vaguely remember that these octonionic chains would end after 3 or something, right? Or there's a reduction at some point?
No, when you get to the 6th one, you've exhausted a particular chain, in the sense that you get to the CL06 at that point, then the next element starts repeating.
Right.
So,
okay,
but you could have 6 of them.
Okay.
Now, can I just say
please.
something? It enables me to show my very last slide. So at the bottom here, you'll see I've said I've identified larger spaces which work via direct multiplication of the octonionic chain objects, rather than the cross product, not the cross, the commutator product, yes. And the commutator product is natural because that's the Lie algebra way of doing it. But if you step outside the Lie algebra, then you can get much bigger spaces. And via this direct multiplication of these objects, and I'm absolutely certain I can get 3 lots of 64 working extremely well, right? And I seem to have found a full space of 512 objects. And that 512 could be enough to get in the biggest exceptional group, which would be extremely exciting. So although your starting point was it stops after 3, actually you can go a lot further.
Right, and then by multiplying these octonionic chains directly under what product is that?
The geometric.
The geometric product still. Okay. Yeah, that also answers my other question actually of how we get to such high dimensional spaces.
Well, no, I shouldn't have said geometric product. Of course, that's how everything is instantiated underneath. But what I meant was that if you take the mappings which are involved in those chains, this is the way to think of it. It's a map from one thing to another. And of course, maps are always associative, right? That's the key. And so you lose the problems of associativity of the octonions because you rederive things in terms of maps. And then you, instead of using those maps as Lie commutators, you use those in direct products. So it's a product of maps.
Yeah, okay, thank you.
Anybody else have any questions?
It's surely a bit suggestive, but obvious that your algebra, the CL06, is 64-dimensional, and then there are 61 particles.
Yep.
So, obvious question, has anyone talked about, maybe there's another one that fills in some gap?
Yes. So Gording and May, I won't go back to it, but they certainly believe that there's at least one more particle that could be found in their setup. And of course, this is dangerous because you're
talking about experiments.
You're talking about experiments, and you absolutely do not want your particle, your extra one predicted, to be of a type that we should have found by now, because then that's very bad for the theory. But in that context, they're doing, I mean, as far as I know, it's fine, right? It's not ruled out at the moment. But they're doing a lot better than a lot of these other unification schemes. People who've tried to use much bigger groups for unification, they end up potentially with hundreds of extra particles. And that's even more worrying because you've got a lot of checking and explaining to do about them. So this does look to me quite good because it's really minimal.
Thank you.
Okay. So I think that wraps it up for today. And I'll see everybody tomorrow. All right. Okay, thanks.